Willkommen, bienvenue, welcome, hodor. Good morning. Thanks for coming in to an early session on the last day of the conference. You're truly the diehards. My name is Stuart Marks. I work in the core libraries team of the Java Platform Group at Oracle. Quick introduction. Since this is a retrospective talk, I figured I should give a little retrospective on myself. I was not one of the people who worked on the original Java 1.0. I came into Java sometime after that. But I did work when I was at Sun Microsystems. I did work on some applications using JDK 1.0. And so I think I do have a pretty good perspective on the history from 1.0. And I also worked on various aspects of the Java platform for over 15 years. Personally, before I started working on Java, I was a C programmer. I guess it's hard for me to say I'm a C programmer anymore. But as a C programmer, when I approached Java, it was actually really cool looking at the 1.0 stuff. Now looking back at the 1.0 stuff, I think we have a different perspective on that. And so that's what this talk is about. So I have started a Twitter conversation on the hashtag Java20Retro. I'm not going to be monitoring Twitter during the talk, and I don't have an assistant helping me with it today. But I hope to catch up with Twitter sometime next year. OK, so let's look at JDK 1.0. This is a snapshot of the top-level Javadoc page for JDK 1.0, listing all of the packages. Yes, really, this is all of the packages. And the amazing thing to me about, well, aside from the kind of cheesy-looking GIF image for the header, and that's an 8-bit image, and so if you look at it, it's all pixelated and stuff. Aside from that, the amazing thing to me about JDK 1.0 is how small it is. And so to give you a quick idea of how things have grown, JDK 1.0, this is just kind of what I call a feature count, which is the sum of classes, class members, methods, fields, and so forth. In JDK 1.0, there are about 2,200 of those if you add up all the classes and their class members. And in JDK 8, that was over 50,000. So the platform, excuse me, in terms of API features, the platform is 25 times larger than it used to be. And here's a little graph of that growth rate. It's pretty amazing how large the platform is, or really, in retrospect, how small the platform is. 1.0 was. And then, I'm not going to go over all of this, but this is a quick rundown of the features that have been added to the Java platform since 1.0. And so you can look at these. Lots and lots of language changes, lots and lots of major API changes, and so forth, clearly have changed the platform quite a bit. What I think is also interesting is to look at what has not changed, at least in the technology of the platform. This fundamental idea that was at the very beginning, say, single class inheritance, multiple inheritance of interfaces. That's still very much central to Java's object orientation. Strings were and always have been immutable, garbage collection, dynamic linking. I mean, these, we deal with these every day. Well, maybe garbage collection we don't forget about, but dynamic linking, sometimes we have to remind people, everything in Java is dynamically linked. And so that has some implications about things. So a lot of these things have not changed. And it's, I think, a testament to the staying power of Java that some of these core fundamental features have not changed and are still serving us well today. But what I did want to talk about is, I mean, certainly there have been a lot of changes in the platform. Some things have changed, but many, many significant changes. But also, what has also changed is a little subtle, and I'm going to try to explore today, is how our thinking about the language technology and how our creation, development, maintenance, and usage of APIs has changed. And that's not necessarily a technological thing. It's something that has evolved as we have learned how to make more effective use of the programming language and programming development in general. So I'm going to hit 5 key topic areas in APIs. You can see them here: general data structures, date and calendar, concurrency, synchronization, subclassing, inheritance, and then kind of a grab bag of general issues. All right, so let's start off with data structures and collections. Okay, so in 1.0, there was no collections framework. Remember, the collections framework came in 1.2. So before that, there were things that were aggregate data structures. They weren't called collections at the time. They were vector, hash table, which is where the T is lowercase, contrary to the rest of the camel case convention. And so some of us call it hashtable. Enumeration, which was the way that you, well, iterated over. I mean, now things are called iterators, but enumeration was the way you enumerated the elements of a collection or an aggregate data structure. And then there are these things, dictionary and stack, floating around, which are related to a hash table and vector. So here I have an example code, a piece of example code of how you used vector. So, well, I ain't going to do it now, but when I was actually typing this, I was typing it in NetBeans, and boy, the whole screen was filled with yellow squiggles. It was amazing. But really, you know, the point of this really kind of takes you back. So vector vec equals new vector. Okay, no generics, right? In fact, we didn't even call them raw types. You just had a vector. And so how did you deal with things when you wanted to put things in and out of a data structure? Well, you could put anything in. So here I put in a string and a boxed integer, a double, an object. And then when you get something back out, you always had to cast it down to the right type. And in fact, if the thing did not, the thing does not match the type that you expected, you would suffer a class cast exception. Vector and hash table are still in there, and I'm pretty sure they still get fairly widespread use. But does anybody use dictionary or stack? A couple people, okay. So that's interesting. Maybe you can talk afterwards. I'm not, well, stack maybe I can see, but they're actually replacements for those. Dictionary is kind of weird. Anyway, it's been replaced by the map interface. But I wanted to get into some more details about how to enumerate the elements of a vector. So there's some interesting things going on here. So here I create a vector and put a few strings in it, and then we use the kind of old-fashioned way of going through the elements. Here we have a for loop, but we get an enumeration by calling the elements method, and we keep running the for loop while the enumeration has more elements. And so this is just kind of like an iterator, except the methods are spelled differently. And then we get the next element, we have to cast it to the right type and print it out. But then what I've done in here is I have this little thing that says, okay, if the string we just got equals the word bravo, then remove the first element. Okay, that's kind of interesting. So what's going on here? We are modifying a data structure while we are enumerating its elements. And so those of you who use the collections framework know that there's a whole set of discussion and issues around this. So if you are modifying a collection, one of the standard collections, like an array list, then there's this thing that happens called concurrent modification exception. So if you're iterating over it and you modify it, the next time you use the iterator, you get concurrent modification exception. And so there's a policy there which is called the fail fast policy. It applies only to certain collections, but the point is, in the collections framework, the need for a policy was established and introduced. So the core collections have a fail fast policy, but other collections don't. For instance, the concurrent collections have a weak consistency policy. The point is there has to be a definition of what should happen when you modify a collection while you are iterating it, or here, if you modify a vector while you are enumerating it. So what happens with vector? Well, it's not specified. Now, the fact is, it does something. Anybody care to hazard a guess what happens? Okay, now, maybe a little too early. All right, so what happens is that it prints out, come on, where's my build? There it is. It prints out alpha, bravo, and delta, because when it reaches bravo, the 0th element is removed, all of the elements shift forward, and we skip Charlie. And so then it prints out delta and finishes. Okay. Yeah, pretty, now that's what it actually does. It is not specified to do this, but by experimentation, that's what it actually does. And it's pretty easy to see what an enumeration does is it just keeps track of what index it's at. And if things shift out from underneath it, the index stays the same. All right, now what happens if we insert an element at the beginning while we're in the midst? Let people. Turns out it's an infinite loop. Okay, and I was actually surprised by this, but of course it's quite explainable because we get halfway through, we say, aha, this word equals bravo, we insert, okay, so from your point, we insert something at the beginning and everything shifts over. Oh, the next element is bravo, we insert something at the beginning, we shift it over. And so basically it infinite loops here. So it's not too, I mean, this isn't terribly interesting, but what I wanted to highlight is there is no specification about this. And I suspect what people did was, if they wanted to do this, they wrote programs that might have relied on this behavior. But it's unspecified. And so there's this interesting question of, you know, what if vector or enumeration changed its behavior in this regard? Would that be compatible or not? I suspect that most people would consider it not be, but there's no specification around this. All right, so now I wanted to talk a little bit more about specifications, although actually in the 1.0 timeframe they weren't really called specifications yet. So if you look at the documentation, there is, this is a snapshot of the vector.copyInto method. So it is declared public, final, synchronized, void copy into, and then it takes an object array. And what this does is it takes all of the elements of the vector and copies them into the destination array that you provided. Okay, so the very interesting things here. Synchronized appears in the method signature. That's interesting. Actually, I have a whole section on concurrency there where I'll discuss this issue some more. That'll be later on. It's also declared final. In fact, all of the public methods on vector are declared final in 1.0. And I actually don't know why that is. I'm not sure anybody, well, maybe somebody in the world does. I did some research in the bug database, and when Josh Block was working on the collections framework in 1.2, one of the things he did was do a lot of retrofitting on the older collections like vector and hash table, and he removed the final modifier. I don't know if it was him personally, but the decision in 1.2 was that the final modifier got removed at some point. And the reason given was historical reasons. So it's lost in the mist, maybe lost in the mist of history of why those methods were declared final originally. Okay, so I was talking about specifications earlier. So we had a question about what happens if you modify the vector while you're enumerating the elements. Well, okay, so you can ask some questions about this. What if the array is the wrong type? What happens? I don't know. I would guess you'd get array store exception, but it's not specified. What happens if the array isn't long enough? I don't know. I would guess, and it's just a guess, array index out of bounds exception. Now, here's another thing, which is, suppose you're, well, it's getting a little bit ahead, but vector is actually thread safe. And so there's actually a race condition if you want to copy all the elements of vector into an array, because you need to get the size of the array, but the vector might change size. So I'll actually go into that a little bit more detail later on. But there's some interesting things going on with just this one API. All right, so the lessons from going back here are, I mean, yeah, so the APIs are old-fashioned and they're raw types and stuff, but it really puts in perspective how fundamental the collections framework is and how many advances that made. Even though the collections framework itself is pretty darn old, it really contrasts with the original stuff. And so one of the things that was introduced in the collection framework was a separation of interfaces like collection, list, set, map into concrete implementations. And that's actually a very powerful design pattern. Whereas if you look at the 1.0, actually I don't have a class diagram of this, we have dictionary and hash table extends dictionary, and those are classes. We have vector, and we have stack extends vector. And actually, I have some more comments about that later on. But the class hierarchy was all about classes and concrete implementations. There was no notion of using interfaces to separate the abstract thought of a linear list of elements or a linear array of elements versus the implementation of a vector. Another thing, as I mentioned before, the collections framework introduced the need to have a policy for concurrent modification. So there's fail fast, there's weak consistency, there's snapshot semantics of things like copy on write array list. That did not exist in 1.0. And I think the collections framework still serves us well today. I gave a collections talk yesterday that was, I think, well received. We're still enhancing it. People are using it every day. There's a lot of work continuing on the collections. Generics, of course, were a big change. Obviously, a big change to the type system, big change to the language. But kind of on a corner of that, which is a fundamental concept of that, is collections very, very strongly became homogeneously typed. That is, everything you put into a collection has the same type. So you have a list of string, and it's a compile time error if you try to put something else in there, like an integer. And you know, in the old days, people would throw a bunch of stuff into a vector of all different types, and that's just the way Java programs were written. And you can still do that today. You have to do some casting and maybe suppress some warnings. You can still put any object into a container because of type erasure. But I really don't see that style of programming anymore. So that, even though you can still do it, we've really moved beyond that. And there's some particular patterns for heterogeneous containers, but those are kind of obscure. The main thing is that this style of programming of putting differently typed objects into containers basically doesn't exist anymore as far as I can see. All right, I'll move on to date and calendar. There's a long and checkered history here. My former colleague Mike Dwigo the other day, if you attended his talk on James Gosling's code, he mentioned that James Gosling was one of the authors of date. One tidbit I didn't know was that the date class, which everybody hates now apparently, they hate it almost as much as they hate calendar. The original purpose of that was to be an object that represented a date and time string, or a date and time object in an email header or an HTTP header. And so that's, if you look at the email stuff, there's RFC 822. It has a specific format for the date, and that's what the date class was intended to represent. But when you put it in a general purpose platform, what happens is there are enormous pressures to enhance it and to do a bunch of other things, right? And so people, if you say the date class is for email headers, maybe it's perfectly fine for that. But if you're looking for general purpose programming, it is totally inadequate. It mixes all these different concepts together. So in particular, the date class represents a single point in time, you know, the usual millisecond offset since 1970. But it also has embodied in it the notion of a calendar system. And so many of us are used to the Gregorian calendar system, 12 months in a year, leap years, and so forth. But for international purposes, people around the world use different calendars. And so the system needed to support different calendars other than the Gregorian calendar. And that was baked into date. And then the date class also has parsing and formatting stuff baked into it, which is really centered around RFC 822, that is email headers. So in 1.1, calendar and Gregorian calendar were introduced to replace date, and in fact at the time most of date was deprecated because all of those things were, had those problems I mentioned. So the idea was, okay, the calendar class is supposed to be the root of class hierarchy that is intended to be able to represent any calendar system. And in fact, it's so loose and flexible and extensible that I would go so far as to say it's intended to support calendar systems that haven't even been invented yet. But if you look at the API, it doesn't have a setter for a month and a setter for a day or whatever. Its fields are all named by integers. So there's a bunch of constants for setting the day, a bunch of constants for setting the month, or setting that you use in the setters and getters. But there are a bunch of problems with this as well, because calendars are complex systems, and that API leads you to believe, oh, I can set all these fields individually, and indeed you can, but there are some very, very strange consequences that result from setting up an API like that. And I have an extended example that shows some strange properties. Meanwhile, it also has some idiosyncrasies. As a carryover from the old Unix C library, the months are 0-based. So January is 0, February is 1, and so forth. And this throws people constantly. In fact, when I was writing the test program, you'll see it's like, wait a minute, that's not right. Oh yeah, months are based on 0. Okay, so I think it still bites people to this day. Okay, one thing about the calendar class is that it is mutable. So So now I don't know. I mean, I think the idea of immutability has really has really. I mean, there are times to have things mutable and immutable, but I think at this point in time, in the present day, people really understand the advantages of immutability. But if you're a C programmer in 1996, it's like, what? Immutable? You mean you can't change it? Why would you ever want to do that, right? I mean, the concept almost did not exist. I mean, strings were immutable in 1.0, but the idea of immutability is a general purpose programming style and APIs that only offered read-only access and things like that. It was almost a completely foreign concept. And this traces its roots back to the early days of a bunch of C programmers migrating to Java, not being used to it, but also the immature technology of memory allocation and garbage collectors and so forth. And so if you're a C programmer, you might say, memory allocation, expensive. Okay, so let's reuse memory as much as possible. So that also led to a bunch of lousy programming patterns like object pooling instead of relying on the garbage collector and so forth. But what I wanted to talk about here is not only is the calendar object mutable, but the individual fields can be changed. Well, the fields can be changed individually, even though it might not make sense to do so. So here's my example. So it's sort of two columns. On the left half is a really pretty simple program that it's intended to do something. It's intended to do something pretty simple. Let's start off with a calendar representing calendar object representing January 1st, 2015, and then what I want to do is set the fields of this calendar object so that it represents February 29th, 2016. Okay, so 2016 is a leap year, so the February 29th is a valid date only in that year, but not in non-leap years. Now, just for purposes of the example, what I'm going to do is set the day of the month first. And so notice I'm using constants here instead of, I'm not saying set the, there's no method set day of month, so I have to say set, and then I name the field using day of month, which is an integer constant. It's not an enum. Those weren't introduced until later. So I set the day of month to the 29th. Then I set the month to February. It's like, well, now I think I have a date that represents February 29th, 2015, which doesn't exist. So what's supposed to happen? But I'm going to charge ahead and then set the year to 2016 and then print it out. And what do you know? February 29th, 2016. Okay, that works. How did that work? Well, I guess maybe there's an invalid state in the middle there, and maybe that's okay somehow. All right, so in the program on the right, I do exactly the same thing. So I start off with January 1st, 2015, set the day of the month to the 29th, set the month to February. But then, oh yeah, so what is the state of the calendar there? I'm going to go print it out. Oh, what do you know? It says March 1st, 2015. How did that happen? Now I go set it to 2016, and it says March 1st, 2016. So what happened there? So there's this weird suspended, it's kind of like quantum superposition state inside of the calendar class where you can set fields and it says, oh, well, my state is invalid, but it might become valid if something else gets set subsequently. But if anything needs to look at this state, I'm going to have to normalize myself before printing it out. So it turns out that getTime gets a date object out of a calendar, and that's the easiest way to print it out. So getting the time out of it forces the calendar to normalize itself, and it has a side effect of changing what the actual field values in there. So it's like, wow. So if you look at the let's see, I think yeah, this is basically the deal here. So there's this weird interaction between the fields and side effects at unforeseen times. Now, it turns out that this is a very strange behavior, of course. So in order to deal with this, they added a mode to calendar that says, oh, okay, well, this is potentially a source of errors. So they added a strict mode so that instead of doing this silent normalization process, it would throw an exception if you actually had some fields. Now, you can still set fields into an invalid state, but if anything tried to use the calendar in that state, it would throw an exception. But the mode is lenient by default. So it's like, wow. So anyway, there are these weird order dependencies and interactions between the different fields. Makes it a very strange and difficult class to work with. And in fact, I mean, not only to use, but it's basically impossible to maintain because there are so many programs out there that depend on all these weird idiosyncrasies and interactions. If somebody tried to fix a bug, it would undoubtedly break somebody. So anyway, so at this point, the calendar stuff has all been abandoned, has all but abandoned and replaced with the java.time API that came in Java 8. Much, much nicer API. Good deal of thought went into it. But anyway, so this is the state of the calendar API. So anyway, and then another thing they had to do was they realized, okay, yeah, there's this nice framework for setting individual fields, but you know, it kind of doesn't work. And if people need to set, say, month, day, and year all at once, then okay, so we'll have a method that does that too. So it's a convenience, but it also makes sense because it's a single state transition that goes to the right state instead of individual fields that potentially can lead through invalid, temporary, transient, invalid states. All right, so there are a few lessons in here. I mean, it's easy to poke fun at Calendar, and I don't mean to. The fact is, it was designed in a real hurry. I spent some time talking to one of the designers about it, and he was a little defensive about it, even still. But the fact is, they tried to do a bunch of stuff, and they had to write down an API. And you know, the fact is, nobody at the time knew Java very well. I mean, basically everybody had less than 1 year of experience with Java. I mean, think about that a little bit, right? Design an API and send it out there to millions of developers, and oh, by the way, you can't change it because of binary incompatible. So design in a hurry and repent at leisure. So anyway, yeah, so a bunch of things going on here. We have mutable state, but we have also a bunch of different fields, and in fact, an extensible set of fields that had all these weird interactions with each other. And that's kind of a toxic mix for compatibility. And I wouldn't try to map out the state machine of Calendar. It's incredibly complicated with a whole bunch of special cases. And it was intended to be designed for subclassing. And I think there's one subclass of Calendar in the public JDK API, which is Gregorian Calendar. There are a handful of subclasses internally, but it turns out the relationship between the class and its subclasses is very tightly coupled. So it was really not a successful subclassing interface, which is probably because it was designed in a hurry. And actually, initially there was only one subclass. So there's a design lesson embedded here as well. If you want to design something for subclasses, or subclassing, make sure that there are two different subclasses that have different forces acting on them. If you have only one, then you kind of have to think about, well, what if somebody in the future did this? And you have to make a bunch of hypotheses about what other subclasses might need without having written them, and you're likely to guess wrong. All right, so let's move on here. Okay, concurrency is an interesting topic. Bit of history. So Java's concurrency mechanism is descended from Mesa-style locks from Xerox PARC, which in turn are descended from Hoare and Brink-Hansen's monitor concept. So basically, locks and condition variables is the main thing. There are some interesting things about Java's implementation of the, not only the implementation, the design and the programming language. So for instance, locking is lexically scoped. So when you say synchronized, when you have a synchronized method, or if you use a synchronized block, then there's no way you can leave that block without the lock being released. And even if something inside that block throws an exception, the lock is released automatically because of the lexical scoping of locks. And this is actually really good. If you've ever did any POSIX threads programming in C, then you really have to keep track of what locks are made where. And a typical thing is you take a lock at the top of a method. Maybe in the middle you encounter some condition and you return. If you forget to release that lock, your system just grinds to a halt because nothing ever releases the lock. So that's one thing where Java was, at the time, Java was lauded. Oh wow, Java's really cool. It has programming language support for concurrency, and I think it's an interesting feature and pretty useful, but there's some limitations with it. There's runtime support for making sure that wait and notify on a condition variable is made at the right time. So that's another thing with POSIX thread. There's this curious relationship between locks and condition variables, and if you get it wrong, things just fall apart. Whereas at least in Java, there's kind of a fail-fast here. For instance, if you want to wait on a condition variable, you must hold the lock that is associated with that condition variable. So that's how all of these schemes work. And so you can call wait on some arbitrary object, but if you don't hold the lock on it, the system's going to say, hey, you don't hold the lock, and then it throws illegal monitor state exception. So that's kind of a fail-fast way of flushing out kind of syntactic level bugs, although there's no way that particular restriction is enforced through the syntax of the language. So that's enforced at runtime. Now there's a simple library API for threads. You create a thread object and you can say start and join. Oh, you can also say suspend, resume, stop, and destroy. Oh boy. Okay, so those it turns out were impossible to use safely, and those have been deprecated. I think that those became deprecated in the first round of deprecations in JDK 1.1. So there's clearly some things going on there where, of course, there's people who claim, oh, we absolutely have to have those. You can't take those away. And then there's other people who rightly say it is impossible to use these safely. So there's lots of interesting things going on with threads here. So now there's some limitations and issues with the way that Java dealt with concurrency early on. And in fact, we still have these today. Every object has a lock and a condition variable associated with it, or at least potentially. And so it's sort of, well, okay, so if you're designing a system where you expect that there are threads running everywhere and everything is supposed to be thread safe, then of course every monitor needs to have a lock in order to protect its own state. And that turned out to be a mistake because, one, there are lots and lots of objects that are only ever created, used, and well, not destroyed, but released by a single thread. So they are thread confined. So there's extra overhead associated with having a lock and condition variable on every object. Now modern JVMs they do a pretty good job of lazily creating locks and condition variables, but all the machinery has to be under there, and that adds complexity, maintenance cost, and a little bit of runtime cost, because if anybody ever takes a lock on an object, then that object is inflated, so it has a larger header and extra things allocated, and that's irreversible. So it turns out that the programming style is that if you want to do locking, you actually create dedicated lock objects and keep them private. I think it's mostly a style of programming that is falling into disfavor is to use the public lock on an object. And actually, that's the other thing, which is that the lock and condition variable on an object are all public. So, we've learned about encapsulation and data structures, and you should, keep your internals private and keep those separated from the callers. But if you're doing thread safety and locking, you might think, okay, so my locking policy should also be private. But the lock on every object is public, and it's public in the class object, and so you cannot restrict the access controls of an object. So any caller from outside can just take your lock and hold it, or notify your condition variable. And so that kind of breaks encapsulation when it comes to dealing with concurrency. There's also a feature of Java that is somewhat controversial. There's two camps in this. But basically, all locks are reentrant. That is, if you have a thread that takes a lock on an object, and it does some stuff, and it calls another method that takes the lock on the same object, then it is permitted for a thread to take the same lock on the same object. In fact, they're well-defined semantics. If you then wait on that object's condition variable, even if you've taken the same lock multiple times, all of them are released. And then when you come out of the wait state, all of those locks are relocked. So there are times when that's really useful and convenient, and there are times when it really leads to sloppy programming. And it's a bit too detailed for me to describe in detail about why that is, but that controversy still exists today to a certain extent. But I wanted to talk about thread safety. So I mentioned earlier that Vector was a thread safe class. So is hash table. So is string buffer. So the early data structures were all thread safe, and that was considered a good thing. And the way they were made thread safe was by declaring every method on them to be synchronized. Well, that's what you do. You have a method that mutates the state. Obviously, it needs to be synchronized because you want to protect against multiple access from different threads. And this works for simple operations, right? So if we're adding an element to a vector, so sure, we have a synchronized method add, so it takes the lock, does its bookkeeping, maybe reallocates the internal array if necessary, does whatever it needs to do, and then returns and releases the lock. Okay, so that's great. Unfortunately, there are lots and lots of things that real programs need to do that are not quite so simple. There are higher level semantic transactional operations that need some kind of consistency over a data structure, and you don't get that by locking every individual method. So for instance, here is an example of enumerating over the elements of a vector. And suppose you have multiple threads that want to do this at the same time while other threads are mutating the vector. This is totally unsafe, right? So there are several individual methods that are thread safe. It turns out the enumeration methods also are synchronized. So basically, when we enumerate over a vector, we're getting each element at a time, and it's taking the lock and unlocking it, taking the lock and unlocking it. But between the locking, something can shift out from underneath. So we get exactly that problem I showed on the earlier slide, where if some other thread modifies the vector concurrently, you could either miss elements or get an infinite loop or something unforeseen. So the way to do this is say, oh, that's right. The lock on every object is public, and so we can actually take advantage of this. So the way that you enumerate the elements of a vector safely as the caller is to write your own synchronized block around the whole thing. So you create your own transaction concept by taking the lock and then doing whatever you want. So you can iterate over it, you can add and remove elements, what you want. But basically, you wrap everything in a synchronized block. So that really exposes vector's internal locking protocol to callers. And so earlier on, I also mentioned there was a race condition with copy into. So the problem here is I have a vector with a certain number of elements, and I want to copy it into an array of the right size. Okay, well, I can say, get the size of the vector, allocate the array with that size, now copy into it. Well, but between those two lines of code, the vector could have changed size, and so there's always the potential that the array that I've allocated is now the wrong size by the time I pass it to the copy into method. So the way to do that, once again, is to write your own synchronized block around the vector and then do that kind of as a transaction to make sure that other threads, so presumably other threads are going to be doing the same thing. So, well, actually, the methods themselves are locked using the same public lock that on vector. So that should be a thread-safe transaction. But the fact is, this is a terrible way to program, right? The idea is that vector is supposed to be thread-safe, but you as the caller have to do your own locking around it in order to do anything interesting with it. So that's kind of a lousy way to program to a library API. But that has a few consequences. So one is it takes advantage of what many people think of as a misfeature, which is that all locks are public. But then it also implies that locking must be reentrant, because if the caller can take the lock and then call methods that also take the lock, then if the lock isn't reentrant, then that simply fails. If you take this to its logical conclusion, the idea is if you have not only one object, but maybe a whole data structure of objects, like a tree of components in AWT, if you want to do a transaction over that and do some surgery on the structure of the component tree, well, why don't we have a getter for the lock? And so the caller is supposed to get that object, write a synchronized block around it, and then it can do surgery on the tree and then release the lock. And so that is really exposing your locking internals to the caller, but it puts a lot of responsibility out onto the caller to get things exactly right. And so that's really, quite frankly, it's a lousy way to program. So there are a few lessons from here that we've learned from 1.0. One is that synchronizing every method doesn't achieve thread safety. There's a lot more going on that you need to think about. I forget when this was, it was in 1.1, there's this idea that synchronized was part of the specification, and that changed. Later on, if you look at current Java docs, you'll notice that even for synchronized methods, the synchronized keyword does not appear in the specification. And so after some thinking, people realized the locking policy, now the the locking policy of an object is actually an artifact of its implementation. Whether or not an object is thread safe is part of its specification, but the fact that this method happens to be synchronized is not part of its interface. And so that was not true early on. So in 1.0, we saw synchronized methods with the synchronized keyword appearing there, and then later on that disappeared from the Java doc. And then finally, I think that this idea of shared memory multi-threading with locks and condition variables is really just too low level for general purpose concurrent programming. And so since then, we've had the concurrency utilities that came in Java 5, some higher level data structures with nicer transactional operations. And then more recently, of course, we have the parallel streams, the streams API in Java 8 that has some fairly convenient automatic parallelism with it. So we've moved on a lot since locks and condition variables. Okay, a few words about subclassing and inheritance. I think in the mid-1990s, object orientation was shiny and new, and everybody wanted to, oh, this is really cool. Let's use inheritance and subclassing. And so the way I describe this is everybody wants a system that is flexible and extensible. And in the object-oriented world of the 1990s, the universal solvent for achieving flexibility and extensibility was through subclassing and inheritance. And you see that in the way that a lot of the APIs were designed. Unfortunately, this led to what's called the fragile superclass problem, where, and I don't know why it's called the fragile superclass problem, because it's actually the subclasses that get broken. So the typical thing is if you have a class and then somebody subclasses it, if the class gets modified in a particular way, that can easily break subclasses because they're essentially depending on behavioral internals of the way the superclass is implemented. Now, if you combine that with Java's goal of achieving binary compatibility, what it meant was that it was, at a certain point, it was very easy to get yourself into a situation where you could not change anything without breaking any of your subclasses. And I mentioned this was an issue with Calendar. It was also an issue with both of the UI libraries, particularly AWT and Swing. Those allowed uncontrolled subclassing. In fact, they encouraged subclassing. The 1.0 version of AWT, the only way to add behavior to the system was to subclass component. Remember that? Remember the old event model before listeners? You subclassed and overrode, I forget the name of the method, but basically you subclassed and overrode methods in order to get customized behavior. Since then, I think people have wised up a little bit. Alan Snyder, who wrote a bunch of object-oriented papers in the 1990s, basically came out and said inheritance breaks encapsulation. And then Josh Block, the author of Effective Java and also the designer of the collections framework, said in the book Effective Java, he has an entire item that is entitled "Prefer Composition to Inheritance," and I think that's a good lesson. I still see inheritance overused from time to time. But you can see this in the APIs here. I think this is one of the deepest class hierarchies here. We have object, dictionary, hash table, properties, and provider. Now, provider is not well used, but it is a fundamental part of the system. That exists in the security package, and we've broke ourselves with the fragile superclass problem a couple times. Some things changed with hash table at one point, and it broke provider, or it actually broke some invariants that provider had. And you know what? Since provider is part of the security language, since provider is part of the security package, if you break the invariants of a critical security class, you have security holes. So that's a pretty big deal. Another issue is that properties, the intent of properties was to be a mapping from string keys to string values, and you have a property file, and it's just a text file, and you can edit it. But properties inherits from hash table, and there's no restriction on hash table to just strings. Remember, no generics, no raw type. It's all raw types. So people would create a properties object and put objects of any type in it. And it's legal to do that. I hear of people who use the system properties object as kind of a global bulletin board for posting objects of any type. Now, there's this problem, which is if you load and store properties to and from and to a file, those implementations expect to have only strings. So there's a bunch of defensive code in there to say, oh, well, what do we do if this thing is not a string? Because it really totally breaks the model. And the reason is that this is a violation of the Liskov substitution principle. There's this idea that if you have a subclass, that subclass should be usable anywhere the superclass is. And that's not true with properties in hash table. All right, there's another example here with vector and stack. I'll just say that stack, if you look at the methods that stack adds, it's a nice stack abstraction, except that it inherits every single method of vector. So you can have a stack that you can modify anything anywhere on the stack instead of just at the top. So it's kind of a weird beast. So what you have to do is, if you're really using a stack, you have to ignore a bunch of methods on it if you want to maintain the stack abstraction. There's some other weird things about object design in here. So the I/O classes are what I describe as a curious mixture of inheritance and composition. So if you look at this whole family of input streams, every little bit of functionality was a new stream, and then you wrap them in each other. And so typical code is, you see at the bottom, you open a file with a file input stream, wrap it in a buffered input stream, and then wrap it in a data input stream to read data out of it. I think it's beyond the scope of this talk to propose a redesign here, but you might think that a family of interfaces and factory methods might do a better job at this. In particular, a file input stream, there's nothing special about the input stream you get out of a file. It's just that its origin was a file. And so maybe there doesn't need to be a class called file input stream, because once you've opened that file, there's nothing really special about it. There are a couple things floating around in there in Java util. There's an observer-observable pair. Does anybody use this? Does anybody remember that these classes are there? Yeah, maybe talk to me about that. I look at it every time I've tried to use it. It's like, wow, boy, how can you possibly use this? The big problem here is that observable is a class, and the reason it's a class is because there's the machinery in there to maintain lists of observers and to notify the observers. And so they said, oh, well, this has to be a class because we want to share this code. But if you're writing some other class somewhere else and you say, oh, I want to become an observable, well, you already exist in your own class hierarchy, so you can't mix this in somehow. So it turns out to be very difficult to use in practice. All right. Oh, I'm sorry. I actually might have misspoke before. The actual title of Josh Bloch's item in Effective Java, in the book Effective Java, is Design and Document for Inheritance or Else Prohibit It. And I think that's good advice that he wrote several years ago. I think it still applies today. And you can see that because it's a reaction to some of the early API designs in Java 1.0. And then I think there's a more recent idea, which is thinking about families of interfaces and static factory methods for getting instances of them instead of exposing new concrete classes for different specializations. All right, a few general programming notes here. In the early days, there was this idea that took hold, which took many years to dispel, which was that Java is slow. And in fact, in 1.0, it was pretty slow. So there's no question about that. And but the reaction to the system being slow was that a whole crop of poor programming practices developed to work around the slowness. So for instance, here is here's an example of a poor coding practice, which is using an exception to break out of a loop. So if you think about this a little bit, if you want to iterate over the elements of an array, it's pretty easy to say, start off with an index variable and then check to make sure that every time through the loop, the index variable stays within bounds, and then you terminate the loop. But somebody observed, well, that's redundant because the JVM always checks the array bounds anyway. So we can take out that extra check and let the VM do the work for us. And And then we just catch an array index out of bounds exception because that means we ran off the end of the array. So we can save an integer compare by doing that. And somebody had some benchmark that actually showed that that was faster in the 1.0 classic VM interpreted bytecode and so forth. Well, it turns out that well, I mean, I guess it was when JIT compilers came in. Turns out JIT compilers are really good at optimizing simple code, and they're really bad at dealing with things like non-local flow control, like exception catching. And so the optimizers could say, if you had a straightforward for loop over indexes, they would say, oh yeah, we know about this. We can unroll the loop. We can do all kinds of nice things. We can inline things. We can make this go really fast. Oh, it relies on exception handling. Let's fall back to the old slow path because we have no idea when the exception is actually going to occur in here. And so in fact, I think at its best, this style of programming was a tiny speed advantage. At its worst, it made your code abysmally slow compared to straightforward, simple JIT optimizable code. I mentioned earlier that since GC was slow, so people would create object pools and say, oh well, we don't trust. You know what it is? It's trust. We don't trust the garbage collector, so we're going to do our own. Remember, these are C programmers in the 1990s, right? And I'm one of them. Yeah. Well, maybe. So anyway, but as time has gone on, I think the systems have become much more high performance, faster, reliable, and so these concerns have fallen away. Something that is, I think, a pragmatic decision early on that we still live with is this divide between primitives and objects. And if you follow Brian Getz's keynote, his talk about Valhalla, we are finally trying to bridge that gap. And it's a lot of work, and it requires a lot of technology to do so. But this is something that we deal with on a regular basis. I think it's a little too easy to say it was a mistake. We should have been like Smalltalk and made everything be an object or something like that. But I think that the fact that primitives were put into the language at the beginning was kind of a bone that was thrown to C programmers. Otherwise, C programmers would have said this system is far too slow. I think it did actually provide speed advantages early on, and for many things it still does. In fact, in the streams library we introduced in Java 8, there are primitive specializations for int, long, and double. It would have been nice not to have had those, but the fact is having those handwritten classes that deal with primitives differently from objects excuse me, provides a significant speed advantage. So primitives, as much as there's this discontinuity between primitives and objects, primitives in many cases still provide significant advantages. But we are finally working on that. Let's see, what else is there? So there are weird, okay, so kind of in order to try to bridge the gap, so instead of there are primitives and there are objects, and then there are boxed primitives, which are objects that are duals of the primitive types. And those, those are sometimes useful, but what it meant was that there was a set of APIs for converting between primitives, actual primitives, and boxed values. And if you look at old code, I think for straightforward things this was okay. If you wanted to put integers in a list, then you had to box the integers and put them into a list, and that was moderately painful. One thing though that it encouraged, which I still see in looking through old code, is the fact is that primitives are just a value. They can never be null. Whereas every object is a reference to an object, and it can be nullable. And so I ran across some old code that used a boxed Boolean value as a tri-state, right? It could be null, true, or false. And I have a piece of advice for you. Don't do that. And actually, it's a real problem because in Java 5 with auto-boxing, you can deal with boxed values pretty conveniently, almost to the point of forgetting that you're dealing with a boxed value. And if you do that, and that boxed value happens to be a null reference, then you get a null pointer exception out of something that is totally nonsensical. So really, I mean, It's terrible. And then there are also these subtle things too, which is, for instance, this line at the last part of the slide. It turns out that there is a specified caching behavior of boxed integer values, but not all the integers are cached. So if you say integer value of 1,000, that will create a boxed integer, and it is. Sorry, let me step back a little bit. If you have two boxed integer values, if you have a less than or greater than comparison, the auto unboxing will say, oh, okay, he wants to do an integer comparison of those. Do unboxing and then do integer comparison. But if you say, oh, well, actually, I don't want to do a less than comparison. I want to do an equals comparison. If those are boxed values, you don't get a numeric equality comparison. You get a reference equality comparison. And now, all of a sudden, this idea of having boxed values is now, gee, I have to realize when I might have two different instances of the boxed integer 1,000. And so in this case, if you say integer.value of 1,000 reference equals integer value of 1,000, the answer is false, which is sort of, it's okay. That's a little subtle, but not that unreasonable. Sure, when you're looking on a slide, but if you're trying to debug something at 1 a.m., this is the kind of stuff you forget, and this is a real pitfall of the language, I think. So auto-boxing helped somewhat to bridge this divide, but it also created a set of pitfalls on its own. So immutability, I think I said a few words about this before. Immutability is now much more well accepted as a general programming practice. Particularly, anything that is immutable is basically automatically thread safe. There's now widely accepted. There are a lot of things that were mutable at the beginning. Date and calendar I talked about. AWT has a bunch of data classes like point, dimension, and rectangle. They are mutable, and what it led to was that every time, every getter basically had to make a defensive copy of these, because since they were all mutable, you never knew what the caller was going to do with it, so you had to make a defensive copy before returning it to the caller. So we're still actually working on this. So in Java 8, the new Java.time APIs, all of those data classes are immutable, and so that was a key aspect of that design decision. And I think people look upon that very favorably. To this day, the core JDK does not have immutable collections. There are a variety of libraries out there, third-party libraries, that do provide immutable collections. But maybe in JDK 9, if you saw my collections talk yesterday, I talked a little bit about this. Maybe in JDK 9 we will get our first taste of immutable collections in the core libraries. And then there's something that John Rose, the JVM architect at Oracle, has talked about, and I don't know if he's talked about it here or in other conferences. He has a bunch of ideas around, he's calling arrays 2.0, which is essentially an immutable array. There are times when that's very, very useful. And the fact that all arrays are modifiable in Java is actually sometimes a big problem. So doing defensive copies of large arrays is quite expensive. Wanted to say a word on specification versus documentation. One of the things that happened, I'm not sure exactly when it was, maybe 1.2 or so, was the idea that it wasn't just documentation that was produced by JavaDoc, it was actually a specification. And there are two things that happened to that. One is the text in the documents became much more verbose because lots more was specified. So here is, I'm not going to read all of this, but you can see from the volume of text, vector.copyInto just has one line, and I asked a series of questions about it earlier that were not answered by the documentation. All of those questions are answered by the collections list.toArray method. So it's very well specified exactly what happens especially if the array is not the same size as the number of elements in the collection. And so one is it gives more information to programmers, clearly, but the other point is that having a specification enables a test suite to be written for conformance testing which then enables independent implementations of Java to be made. And in fact, there are independent implementations out there, and this is what the licensees use for testing conformance. All right, so I'm just about out of time, but I'm almost at the end here. This is basically a recap of what I just said. So I wanted to summarize here with this quote from George Santayana: "Those who cannot remember the past are condemned to repeat it." I think there are a lot of lessons to be learned from looking at the history of Java. We've learned a lot since then. We've made a lot of mistakes, and so let's not repeat them. But I would not like this to be me up here saying, boy, those people who designed Java were so stupid. Look at all the mistakes they made. So I wanted to show you another quote from George Santayana, which is not quite as popular as the first one. "We must welcome the future, remembering that it will soon be the past, and we must respect the past, knowing that it was once all that was humanly possible." And so I hope that 20 years from now, when people look back on the work we're doing in Java today, they forgive us our mistakes and say, look how far we've come since then. Thank you.
Could I ask you a favor? If there is a seat next to you, could you please raise your hand? Okay, that's great. So about 1, 2, 3, 4, 5, 6 seats. Thank you. All right, let's get started. Welcome to the session on a few hidden treasures in Java 8. My name is Venkat Subramaniam. We're going to talk about a few things that I've found to be fairly interesting in Java, and we'll look at some of these features, take a look at how we can use it. So one of the things that really got excited me about Java 8 is some of the elegance it provides. First of all, the code ends up being a lot more concise. Not only is the code concise, we'll also be able to express our intent very clearly. With that comes along ability to write code with fewer number of lines of code, but fewer mutable variables. As a result, also code that seems to have a lot less errors or less error prone in general. So I want to look at a few different things we can do to get our lives easy or easier in terms of getting some common tasks completed using Java 8. Some of the things that I've run into that are pretty interesting and useful. Let's take a look at one example first of all, and I can bet you that everybody in this room has done this at some point in time or another. Let's say for a minute I have a current directory here. Let's start with a current directory, a new file. I'm going to provide the location, let's say users. I'm going to just simply specify my directory here called a dir, and I want to be able to get some content out of this particular directory. Well, obviously this is going to be a Java I/O, so I'm going to bring that in. But I'm really interested, let's say, to list, let's say, print the files. So we are said, print the file names, comma separated. So that's basically what we are asked to do, is to print the file names, comma separated. Well, how do we go about printing that? Well, in the traditional approach, of course, we would use a for loop to do this. So we could start something along the lines of, for instance, we can say file, let's say, children equals to, and then we could say, in this case, current directory. and then list files. So this gives us all the children. Well, it could be potentially empty. So I'm going to say children is not equal to null. But then, of course, I would start out by saying a for loop. Well, in this case, I don't want to really write nasty loops here. So we could simply say something like file child coming from children. And then, of course, we could simply output the child.getName and get the value out of it. Well, as you can see here, I don't use any slides. I'm just writing code. But if you're interested, you can download these examples from my website. I'll post this right after this talk, so you can download it just about any time you want to. So I'm going to loop through and print this information. And sure enough, in this case, I'm going to loop through all the values in this directory and have that printed out. Well, how do I go about printing these values after all? Well, I've got all the list files, and once I get the children or all the files from the directory, I want to get through each of the children not equal to null and get the values and print out. Well, we could go through this and try to get the values out. Let's see what it's telling us. Well, some reason it's not printing. Anybody sees the error here? So I want the files. Let me make sure there are files in this directory. That would be nice to have. So let's go to the users, and then, of course, the Venkat directory. Oh, of course, I misspelled it. That's why. That's nice. So it didn't give us an error, but it was null. Great. So you can see in this case, I got the two files. Well, unfortunately, though, you can see that the files really were printed, but not comma separated. How do I really make it comma separated? Well, that shouldn't be really that hard, is it? So we can simply put a comma right there. Well, but it's on two different lines, not on the same line. That's kind of silly. Let's fix that. Let's now do this. That's awesome. Oh, but wait a minute. There's a stupid comma in the very end. Anybody else seen this problem before? Every one of us, right? And how do you feel when that happens, right? And then you think about this for a minute and you say, I got a great idea. I can create the string. I can strip the comma out of it. Well, after a while, we realize the string is immutable. Then we reach out for string builder, and then that only seems to drag us in deeper. After thinking deeply for a few minutes, you realize there is actually a very simple solution, and darn it, how did you not think about it? All you have to do really is to simply change this to int I equal to 0, and then I less than, right? And then, of course, children.length, is it length or size or, well, okay, length. And then I plus plus, oh, wait a minute, is it less than or equal to? And all that done later, we can simply come back here and say print. And then, of course, in this case, we will say children, and we can use a square bracket I, obviously, in this case, to print it, to get the value out of it. So we can say that, but what about the value after all? When we run this, of course, that's nasty. We want the name, of course, get name. Well, that's still nasty. Where's the comma then? Then we realize we can simply output, in this case, the comma. Well, but I don't want the comma sitting in the end again, back to the square one. We realize this can be done easily if I is not equal to, and then you say, what is it, children dot, right? And then you realize, is this really happening to you, right? So that's an example of how such a really simple task can become incredibly difficult. Let's try to do this one more time. Let's try this one more time. We're going to say, in this case, bring in a few tools. Let's bring in this case, a stream, of course. So we are interested in a stream. Now, if you ever have a collection like a list, you can call a stream on it and get a stream out of it. But we don't have a list. We have an array on our hand. So we're going to say stream.off, and then I'm going to say children. So this converts an array into a stream by using the off function. You can get it. Now that I have a stream on my hand, I can perform a map operation. I can say file get name, and this easily gets us the name of every single file. And the last step here, of course, is to collect this. And once I collect it, I can simply go ahead and print it, because that's what I really want to do. So let's go ahead and say, in this case, I'm going to go ahead and call a collect function. But the collect I'm really interested in is going to be a collect into a string. So I'm going to say static at this point and say collectors, and bring in the collectors function into the mix. And so in this case, I'm going to say joining. And then, of course, I'm going to just put a comma in front of it, and you can see that it prints out. So the day I learned about joining, I cried that night. This is the way programming should be, right? So it's amazing how you can actually very simply program by writing code like this. So you don't have to really go through as much trouble when you want to do some simple operations like this. This can be extremely convenient to use, as you can see. So we got the collection of data, did the mapping, whatever we want to do mapping, but eventually we call joining. So this could be your class path you want to join together, whatever that could be, and it's smart enough to patch those values with the joining without, of course, including in the end or either corners, so that becomes a very easy solution to use. So things like off to really take an array to a stream, and then of course your regular filter and map operations, and collect is a reduce operation. In this case, we asked it to collect it into a string using the joining operation and print it out, or get the value out of it. So that's exactly what we did here. So that gives us an idea about how we can use some of these operations. We learned about off and we learned about the joining as well. But what about interfaces? Now, interfaces are a little special in the case of Java. So let's take a look at what interfaces can be in Java, which is a little weird if you think about it, but it's pretty powerful. Now, step back to Java for a minute. Think about what they used to do in Java. Well, if you have an array and you want a utility function on array, where would you go to? You'll go to arrays utility class, remember? If you had a collection and you wanted a utility, where would you go? Collections. Well, that's exactly what they did when they started developing Java 8. I remember the first few months into Java 8, they had all these things that end with the S in the very end, and very soon they came to sense and realized now they're going to explode the API with all these classes ending with the S compared to these interfaces. And that's not going to be very wieldy at all. And then they realized, wait a minute, why are we doing this? If we are working with a certain interface and we want a method, a utility method related to that interface, why not simply stick that into the interface itself? So static methods can be part of interfaces now. So for example, let's say I have an interface called util, just for an example here, and within this I'm going to write a static method, let's say number of processors, or number of cores, let's say, and I'm going to write a convenience utility method right here. And in this case, of course, I can return runtime dot, let's say, get runtime, and then available processors, and this is going to return to us the number of cores, or at least the one it thinks. And so in this case, I can output util dot number of cores, for example, and I can call that particular method and simply use it. So this shows to us that we can actually reach in and call this particular method. What did I do wrong here? So runtime dot get, is it runtime dot get runtime? Whatever that number is. I know exactly how to fix this. I'll just say 8, that's enough for now. Okay, so that's an example of how we can just call that method right here. So that gives you an idea about how to call static methods and use it, which is really a number. You can change it to even bigger machine right there. It's easy to work with that. So that's an example of how you can call static methods very directly, as you can see. So this can be very convenient because interfaces now can have all these static methods, and you can readily reach into it and use it. So this also is a bit of a challenge at the same time, because what you're used to in the past is no longer the case. Now when you start working with interfaces, all of a sudden interfaces now can have static methods, and you're like, wait a minute, the interface I was familiar with now suddenly has a few new things, which means you got to take the time to learn a few things that may not have been there before in the previous versions of JDK. That's a little bit of a challenge, but I'm sure that's a lot of fun to work with once we get comfortable with knowing where to look for things. So I talked about the static methods that are available in interfaces. You're going to see this all over now. Almost every corner you turn, you can have static methods and interfaces that you can look at. Well, okay, we looked at one example here, but I want to talk about the next one thing that's pretty interesting, which are called the default methods. Now, one of the problems is, remember what interfaces mean in Java. Interfaces establish a contract, and if once you publish an interface, even if you think about modifying an interface, you immediately get death threats over email, right? Because people don't like you if you want to modify interfaces. So on one hand, interfaces are set on stone once you release it. On the other hand, every one of us can agree that we get smarter every day. And we are telling the JDK team that what they did 20 years ago, they are stuck to it. They cannot change it, right? And that's really unfair to say we cannot evolve. So they were really looking forward to how can we evolve interfaces, how can we change it, and so there was a nice little loophole into it, which are called the default methods. Now, what is a default method? A default method is a method you can put into an interface, and we're going to talk about some rules related to default methods, but let's start with a little example. Let's say I have an interface called a fly interface, and in this case, I'm going to write a method here. Let's say in this method is going to be a void. We'll call it as takeoff. Now, clearly, this is an interface, and I'm going to put a little OK here just to show that the compiler is happy with it. But of course, if I come over here, and if I were to implement this method, I'm going to say fly, : let's say, take off. Notice right off the bat, Java is going to complain to me saying, what are you trying to do? You're trying to implement a method in an interface. So until Java 7, here's my definition of an interface. An interface is something that says a lot about what it'll do, but it never does anything. Kind of like my boss, right? So in other words, this is just sitting there doing nothing with a few descriptions as these are things that could be done. Well, that all changes with Java 8, fortunately. You can come in and you can put a little method right here called default, for example, and you can see the compiler is quite happy with it. So you can start defining default methods into interfaces very readily, and I'm going to put a few more things here. So I got a takeoff, I've got a little method called the turn, and I have a method here called a cruise, and finally I have a method called land over here. So clearly you can see I have 4 methods I have implemented: a turn method, a takeoff method, a cruise method, and finally a land method. And the compiler is quite happy with all those 4. But let's understand what happens when you bring in default methods into interfaces. So there are 4 rules of default methods in Java. But before we talk about the 4 rules, let's understand a few differences. When you start putting implementations in interfaces, the first question people often ask is, oh gosh, if you can put implementation in interfaces, how is then this different from abstract-based classes? Well, abstract-based classes can have fields. Abstract-based classes can have implementation or state in it. Well, interfaces cannot have state. Interfaces can only contain method implementation. So if I want to deal with the state, how do I do it? There's a very little nice trick for you to deal with this. So for example, let's say I want to know the altitude of this particular fly or a flight. Well, how would I do this? Obviously, I wouldn't put altitude here as an integer or whatever that is. That wouldn't make any sense because you cannot have a field or a state in an interface. But don't worry, all you have to do is simply say get altitude, and that becomes an abstract method in the interface. And then of course within takeoff you can say takeoff, and you can report whatever the altitude is, and you can get the altitude right there readily by calling the get altitude method. Where would the get altitude come from? Obviously that'll come from the implementor of the interface. So interfaces can have default methods, but anytime they need a state, like a factory method, they push the state down to the derived class to hold the state. So they're up here doing their stuff and then lean down to get the state and do their stuff again. That's a very nice way to really work through it. But coming back to default methods right here, we got 4 default methods given the example. There are 4 rules of default methods. Let's talk about the first rule. Rule number 1. The first rule is any default method is available to you when you extend or implement. So in other words, if you implement an interface or extend an interface, all the default methods are available to you. They are within your reach, which is a nice thing. They're not just stuck over there up in the top. So let's look at an example of that. I'm going to say in this case interface fast fly, and implements in this case a fly interface. I don't have anything in the interface at this time, but my fast fly interface actually has all those 4 methods. It contains the method takeoff, turn, cruise, and land because those methods are obtained through the inheritance right off the bat. We don't have to worry about it. Let's actually see if this is true. So I'm going to create a class called, let's call this as a C-plane class, and it implements, in this case, the fast fly. So we have an implements fast fly, and I don't have anything in the C plane right there, as you can see, but I'm going to come down here and call a method, and the method I'm going to call is called a use method. on the sample. So new sample, let's say new sample.use, and let's go ahead and write this use method. So I'm going to say in the use method, I'm going to call the cPlane. So let's say cPlane, and I will create a cPlane object, and in this case equal to new cPlane, and I will simply say cPlane.takeoff, and you can see right off the bat I can actually call that method and get it into it implements. So you can see that I can bring that in readily and bring that into the interface as much as I want to. So back here, implements. Let me spell it. Implements. So what did I do? Oh, extends, of course. This is an interface, isn't it? Right. Had they kept it in implements, would be consistent, but never mind. Okay. So that's basically, it's never your fault, right? I love this life. So you basically, extend this, and you can say, hey, takeoff. And where did the takeoff come from? It comes through the inheritance hierarchy. So let's try this one more time. I'm going to call the turn method, and I'm going to call the cruise method, and finally the land method. You can see all those 4 methods are here. So we pretty much used rule number 1. Well, then comes along rule number 2. Rule number 2 says you may override any of the default method. So if there's a default method, you can override the default method. Absolutely nothing stops you from doing it. You can do that in the class, you can do that in the interface. It's up to you entirely. So let's go to the interface right here. I'm going to take this method called the takeoff method, and I'm going to bring in the takeoff method, and I'm going to change it to a fast fly right here. So I overrode the method called takeoff in my fast fly. So as a result, you can see when I call the takeoff on the cPlane, it's no longer going to go to the flies takeoff method. It's going to go to the fast flies takeoff method, as you can see. That's rule number 2. So rule number 1, you got everything you have. Rule number 2, you can override what you want to. And then comes along probably the most important rule, rule number 3. But before I talk about rule number 3, let me quickly mention one problem you have when it comes to bringing multiple methods through hierarchy. This is a problem of multiple inheritance. I was giving this talk quite a while ago, and while I was giving this talk, one lady in the audience, she did something really wonderful. She didn't say a word, and she just took her hands and she just did this in front of me for a couple of times, and then she put it down and like this. I'm like, oh, that's awesome. She just showed me a diamond. This is called the diamond problem. And the diamond problem is a very famous problem. Do you know how you know it's a programmer who has programmed in C++? Ask them to slightly remove their shirt, you'll see a scar the shape of diamond on their back, right? That's how you know it's a diamond problem. So everybody who's done programming in C++ has seen this diamond problem, and the problem is when you have multiple base classes, and those base classes have a common base class, well, it ends up being this way, and you got to really bring it down into a diamond, and that's really a pain. Well, but the pain actually comes from not the fact that you have multiple inheritance, but the pain actually comes from the fact that you have multiple inheritance of state. Well, interfaces don't have state, so you don't have a diamond problem on your hand at all. Well, then that brings the question, what if I do have multiple implementations? What do I do? Rule number 3 says any method in the class hierarchy takes precedence over any default method. So in other words, do you have a method in your class hierarchy? Does your class, your base class, your grandfather class, your great-grandfather class, all the way up to object, does that have a method? That method takes precedence over any default method. So here's an easy way to think about it. Your hash code method will never ever come from an interface, because your object has hash code, it's going to pull up object's hash code, or equals from the object. If you override in your class, it takes your method in your class, otherwise it keeps walking the hierarchy of your classes, and only when it exhausts your class hierarchy, it says I couldn't find the method in the class hierarchy, now I'm going to look in the interfaces. That's the last thing it's going to do. So let's look at this example right here to see how this is going to work. So I'm going to create a class called vehicle, and the vehicle has a method public void land, and in this case I'm going to simply output, I'm going to say vehicle : land right here. So you can see that I have a method called land in my class called vehicle, and I'm going to come down here and say extends vehicle. So this simply says that my C plane is deriving vehicle, which in turn derives from object, and then of course I'm implementing fast fly, which again extends fly. However, the rule number 3 says that the land function will no longer come from the interface. The land method will come from the vehicle class because your class hierarchy rules. So if I run this little code, you can see in this case that the land method came from the vehicle class and no longer did it come from the fly or the fast fly anymore. Well, that leaves us the last rule, which is a very important rule to think about, 4th rule. And that says, what if there is no method in any of your classes in the hierarchy? So that's the first rule, right? There's no method in any of the classes in your hierarchy, but there are 2 interfaces with default methods in your hierarchy, right? So in other words, there are 2 interfaces in your hierarchy and they both have exactly the same method. So there are 2 interfaces with a default method of same name, of course, right? So same name and signature. So in other words, what do you do if there are 2 methods in your hierarchy with exactly the same method? Java handles this in a very, very nice way. They say it's your problem. So it's very simple as that. So they say, well, sorry, you go deal with it. So this is something you have to solve. They're not going to help you with this. So in this case, let's take a look at an example here. I'm going to create yet another interface right now. So this interface is called a sail interface, and I have a default void cruise in here. And the cruise method simply says sail : let's say a cruise. So you can clearly see there are 2 interfaces with exactly the same method called cruise and the same name. I haven't brought the sail in here, so there's no problem yet. Everything seems to be fine. But I then go to the C plane class right here, and I tell the C plane, hey C plane, go ahead and implement the sail as well. Now you can see you get a compilation error at this point because you are bringing in another interface into the mix, and that interface, of course, is going to be the sail interface. And what does it say? It says class C plane inherits unrelated defaults for cruise from fly and sail at the same time. So they gave you an error of ambiguity right there because you brought in 2 interfaces into the mix and the methods are colliding. So this becomes your problem to resolve now. So what are you going to do? You have to solve this by, so the way you solve rule number 4 is by bringing in rule number 3, right? Because rule number 3 says anytime you have a method in your class hierarchy, that rules. So rule 3 is often a solution for rule number 4. So what am I going to do? I'm going to simply come back here and say I have a void cruise function, and the cruise function simply says C plane cruise, and you can see in this case we are able to resolve that and use the C plane's cruise function. But obviously the point really here is, but what about the methods in the default? We still want to use them. How do we get to that? Well, thankfully we can. So we can say, for example, if, let's say, altitude, as an example, is greater than 0, maybe, and then else, I can then say in this case, well, I can say fastfly.super.cruise, and I can call the method, and then else I could probably say sail.super.cruise, and I can call the method like that. And you can see that in this case, the C plane's cruise turned around and called the fastfly's cruise. You may wonder why in the world I said fastfly.super.cruise rather than saying fastfly.cruise. And the reason is, of course, you know that cruise may be a static method in the fastfly. You don't want a static method, you want a default method. Now, they could have called it default over here, but if they did, that would make sense, so they couldn't do it. So they had to call it super, so it basically says, go ahead and call it through the hierarchy and call it. So this is, and also by default, they could have said, it'll be a default method unless you say static. but they wanted to be consistent with the way we call static methods in the past, meaning if you just call without any reference in front of it, well, that's going to be a class name or interface name, so that's intuitive. It's a static method, so we say super to say it's a default method and not a static method. So that's why you have to put the word super here rather than just calling it on the fast flight directly. So that shows you how we can use default methods very nicely. And so once again, you're going to start seeing these default methods almost every corner you turn. You're going to see these quite often in the code, and they can be pretty powerful when used properly. That can be a nice design tool as well. Like everything else, we have to be careful how we use these things, but once we use it wisely, this can be quite beneficial for what we want to do. So that gives you an idea about what default methods can do. Let's go a step further and see how we can put these to good use now to do something a little bit better than what we've been doing so far. So I'm going to start out with a little example of a create person. So this is going to create a bunch of people. You can see I got a few people like Sarah, Bob, Paula, Paul, Jack, Jill, and I want to work with these people. So I'm going to say list person. We'll call it people equals create people. And I want to sort these people. So I'm going to say collections.sort people. Anybody who has seen this code before? We all have, right? So what do you think? This is great, this is bad, this is pure evil. Which one do you think this is? Pure evil, absolutely, right? Why is this pure evil? Because it changes the input given to the function, right? Changing an input given to a function should be crime punishable under law, right? Nobody should ever do it. Of course, you may say, if it's so bad, why did they do it? Well, I know exactly why they did it. They were young, they needed the money, right? But now we know this is not a good thing to do because it's going to really mutate the value given, not a very good thing to do. Yes, it gives us better performance, but if you really wanted performance and you don't care about correctness and morality, you should be programming in C++, right? So the point really is, we want to really be doing the right things as well. So how do we go about doing this properly? Well, notice what I'm going to do here. I'm going to go back here and say public static. We'll say print sorted, and this takes a list of person. We'll call it people, but I'm going to pass a comparator over here as a parameter comparator, and this is going to be a comparator on a person. We'll call it comparator. Now, what am I going to do with this? That'll come in a minute. We'll get to that in a second. Let's go ahead and bring in the comparator right now. So I'm going to say java.util.comparator, and I'm going to bring in two things into the mix here. I brought in the comparator, but I'm also going to say static on the comparator. So comparator actually not only is an interface, it's got some interesting methods to it. We'll talk about this in a second. So now that I brought in this code so far, let's see what this code is going to do for us. I'm going to say right now, I've got the value on my hand, so people.stream, so I'm bringing in the stream API. I'm going to call sorted on it and pass the comparator to it, and then for each, I'm going to simply say system.out, and I'm going to just print each of the person after sorting it. So you can see how easy it is to write this code to say, given this collection of people, sort them based on the comparator given, and then once you do, just print each one of them. Well, let's go ahead and exercise this and see how we're going to use this. So I'm going to come down here and say print sorted right now, and I will send in the people to it. But I ask the question, how do I want to sort it? Well, I want to sort it based on the name of the people. Well, name of a person is nothing but a function after all. Given a person, give me their name, that's a function. Well, I want to compare based on that function, so it's a very easy way to implement it. You simply say comparing, and then you specify person : get name, and look at the way this has been organized now. You simply call the function called comparing, and what does comparing do? The comparing function simply says, I'm going to return a comparator for you. Now you know where comparing comes from. Comparing is a static method in the comparator interface that returns a comparator to you. So you call the comparator.comparing, and you get back a comparator on your hand, and you can do the sorting based on that very easily. So you can see how in this case, when we call this method, we are sorting based on the name. Even though in my original list, if you remember, I had Sarah on the top and a few Jack on the bottom, you can see that Sarah is in the bottom right now. because we sorted based on the name, so the sorting is happening based on the name in this case. But let's say I don't want to sort on the name, I want to really sort them based on the age values. Well, that shouldn't be really hard at all. Notice I'm just changing the function to an age right here, and as a result you can see when I run this code, the sorting now happened based on the age and not based on the name. You can see the very first object printed is person with age 2, and the very last object is a person with age 72. Both of them happen to be Jack in this case, the young Jack on the top and the elderly Jack in the bottom. However, there is one small problem in this code. When I ran this, Bob was extremely unhappy. Bob said, "This is not fair. Why is Sarah before me?" So there are two answers to that question. First answer is, Bob, get over it. So that's one way to fix it. Or we can say, well, fair enough, if two people have the same age, it's only correct that we do alphabetical sorting if the ages are actually the same. So we can actually do that fairly easily, as you can see. So a second ago when I ran this little code, you can see that Bob was right after Sarah, who is 20 years old, but I'm going to change this now to comparing based on the age, then comparing, and I'm going to say person get name, and you can see that in this case it's going to compare based on the age first, but if two people have the same age, it then compares based on the name. This appears like fiction when you read this, but it's actually true. As you can see, it actually works. So it's very highly expressive, as you can see. Yes, please. Yeah, you can go to a reasonable extent, as long as you don't lose clarity in the code, you can. So to a fairly good extent. Well, keep in mind, as long as you can get a healthy comparator on your hand, you can do this. So refactor them to a modular code that will return a comparator, so the code doesn't become a nightmare to read, and then just flow through that. Give a nice name for the comparator to logically mean what you want it to be. Then your code is still readable, and you're able to get the result out of it. So you can write your own functions to return that comparator fairly easily as well. So that's basically what you're doing here, is combining these things together to produce a nice result, and that becomes very easy to work with. So that is one example of how you can use the sorting. Oh, quickly, I forgot to mention, you know what comparing really is? It is a static method. So it's a static method that returns a comparator, but you also know what then comparing is. What do you think it is? It's a default method, right? So it's a default method in the comparator. So we are using in this example both a static method and a default method. And you can see the default method is quite charming in this case. It quietly came in and made this work. We didn't have to really call silly static methods over and over. This gives a nice flow through it. So if we begin to. I have to say, when I first came across static methods and default methods, my first reaction was, gosh, this is ugly. And then about an hour later, I'm like, oh, I love this. I have not gone from hate to love in such a fast time at all with any feature, but this is something I begin to really understand and appreciate as well. Please.
If I want to not display some of the fields of the object,
Right.
is there any way to exclude? And the second question is, how do we serialize?
Right.
I want to serialize the first object.
Right. So the question is, how do you remove fields from the person? Well, you can. So I'm going to take this as two different questions. One is, I don't want some people, if they're not meeting a certain quality, then you would apply a filter before you come to sorted. So for example, I would say, I'm really interested not in all the people, but I only want adults to come in. So I can say, given a person, I can say person.getAge is greater than, let's say, 18. This is adult based on their age, not their maturity. So you can actually ask in this case, and you don't have anybody younger than that. That's one way to do it. The other way, of course, is you can say, well, it's really about filtering properties once I get to it. Well, that you have to really change the function you are using here to say whatever information you want to pull out of it. And I already forgot your second question. Oh, serialization. You don't talk about serialization in public. Okay, so so that's basically the way you can do this. All right, so All right, so we looked at how we can do sorting already, which is really nice, but we can go a step further than this. We can actually perform a very nice grouping operation. I want you to just think about it. I'm not going to write this code because I don't want to punish myself here right now, but I want you to just think about this code. You got the collection of people, and I want you to take these people, and I want you to create a hash map. And here's my requirement for you. Your hash map should have keys, which are names of the people, and the values must be the list of people with that name. So let's just go through the mental exercise to think about how we will do this. You first create an empty hash map. Then you take one person from the collection. You take the name. You go to the hash map and say, do you contain this key? It says no. So you now create a list. You add the person to the list. You put this list into the hash map with the key and the list. Then you go to the next. Should I keep going? No, right? Because you know this pain already. That's called Java programming. We have done this. So you're like, oh, come on, there's got to be a better way to do it. Well, thankfully there is. So notice what I'm going to do now. I'm going to come in here and say, here's a list of people. And I'm going to say output, well, people.stream. So we got the stream of people, dot collect. And in this case, I'm using a collect function, just like we did before in other examples. But what I'm going to do in the collect here is, I'm going to simply bring in the collectors that I brought in as an import already. So I'm going to say right here, grouping by, and I'm going to say, in this case, person get name. So I want to group everybody based on their name. So you can see the power of this code. So we have the name as a key value, but notice the values for those keys, they are list of people. So you can see Bob and Bob male 20, but Sarah is a different story. I've got two Sarah in there in the list. The first Sarah who is 20 years old and the second Sarah who is 22 years old. So you can see the collection of people in the list. So you got a map of a string, comma, list people on your hand. You say, okay, that's cool though, but I don't want all the people. I really want to get their age values. After all, I want the name and a value of the ages. So if I have a value called Sarah, oh, what are the ages of all the Sarah in my list? I want to know 20 and 22. I don't care about the people. This kind of goes to your earlier question as well. I don't want all the properties of the person. I just want only those properties. This is another solution for that. So notice what I'm going to do now. I'm going to say grouping by, comma, mapping. So you're grouping and mapping at the same time. And then what am I going to map it into? I'm going to map based on the person's get age. And then I want to put this into a list value after all. So you can see in this case, now we have all the people given to us. And then, of course, once we get the people's name, I want only their age values. So you can see Bob 20, whereas Sarah is 20 and 22. And then you can get the values by doing the mapping very nicely. So that gives you an idea about how you can group and map at the same time. So you can see the power of expressiveness. This is what we call as declarative programming. Declarative programming is where you say what you want to do, not how to do it. So you just issue a command, do this, and you walk away, and the underlying libraries take care of things for you. In the imperative style of programming, we roll up our sleeves and spend the next 2 days writing that code. And here's what happens when you take 2 days to write that code. It is 2 days of coding and 3 years of debugging, right? And that is really a nightmare to deal with. Well, the code you don't write has the fewest bugs in it. And so I'm all for not writing code when I don't have to write code, because the fewer code I write, the fewer bugs I have to deal with. So this is nice to just be able to rely upon this declarative style rather than having to write all that code all by ourselves. So that is about how we can group these together very nicely. Well, let's go a little further now, and we look for a few other beautiful functions we can actually use. So this is one thing that I begin to see in applying with patterns as well, is we can actually nicely start forming good functions together. So I'm going to write a function here called, let's call it as print info. And I'm going to take a value, take a message as a parameter. And I'm also going to take a predicate as a parameter as well. And this is going to be an integer predicate. I'll just call it predicate. So I've got a little function that takes a predicate. Where does this come from? The predicates come from the function package. So I'm going to bring in java.util.function.star. That's where the predicate is coming from. So all I'm going to do is output the value plus the message plus, let's just put a little colon and then plus a predicate dot test on the value. So you can see in this case, I'm going to just print that information out. Well, how am I going to use it? So predicate integer, we'll call it as is greater than 5 equals. Given a value, tell me the value is greater than 5. So you can see this particular predicate is telling me whether the given value is greater than 5 or not. So I can now call print info and pass a value 4. I can say is greater than 5. And then I can then pass is greater than 5 as a predicate to that particular function very easily. So this time you can see that the output tells us 4 is greater than 5 is false. So we pass the predicate to this particular function where the predicate is nothing but a lambda expression. But I can also now say a predicate integer, this time is even equals, and I'm going to say given a value e mod 2 is equal to 0, well, I can simply say print info 4 comma is even, and in this case I can simply say, well, let's say is greater than 5. Well, now this time I'm going to pass to it is even, and you can see that it tells me a true because the value is actually even. Well, but the beauty of this is I don't have to struggle through to do more work. I can say is greater than 5 and even, and in this case is greater than 5 and is even, and I can nicely put them together, and obviously that's a false. It says that it's not true. I can also say print info 4 is in this case is greater than 5 or even, and of course is greater than 5 dot or is even, and we can start combining these things very effectively with the AND operation, OR operation, negate operation, and all those good things. I can put those together very nicely. So this is one thing I'm beginning to use as well when I want to really pass predicates to functions, but I can start combining those predicates, but my function itself is pretty simply using one predicate. Well, I'm just using the decorator pattern here on the predicates after all, so that becomes very nice and concise and easy to work with. I can do the same thing with functions as well. So let's look at an example of that. So notice what I'm going to do here. I'm going to change this to a function rather than a predicate, and this is going to become an integer. We'll call it a function, and I'm going to change this to function.apply. Well, let's give it a try one more time. This time I'm going to say here is my function that I created, and the function integer comma integer says, well, inc, and I'm going to say given an element e, return a e plus 1. Now I can call print info. I can pass a 4 comma incremented, and then I can say inc over here, and we can see in this case it says 4 incremented, well, becomes a value of 5, as you can see very nicely. Well, likewise, I can try one more thing. I can say doubled over here. Well, where doubled is going to be a function we'll call it doubled, and in this case I'm going to return a times 2, and notice in this case it is doubling the value after all, so I'm going to pass doubled to this, and you can see that it says 4 doubled is 8. But once again, notice what I can do. Print info 4 comma incremented and doubled, and in this case I can say comma inc and then, and I can pass this to doubled, so I'm incrementing first and then I'm doubling. So 4 plus 1 is 5, 5 times 2 is 10, and you can see that actually worked just fine. But I can also do the following. I can say doubled and incremented. Well, obviously in this case I want to double first, so 4 times 2 is going to be 8, and then once I get the 8 I want to add 1 to it, should be 9. Well, you could say, you could do this, Venkat, you can say doubled dot, well you can, but instead I'm going to say inc compose doubled in this case, and you can see that in this case I'm actually reversing the order. So notice that here I called and then, whereas here I called compose. So compose will swap the objects and then apply that. You may look at this and say, gosh, why would they want to do that? And the reason is it doesn't disrupt your flow. So if you have a group of functions, but if you want to apply the functions in reverse order, you don't have to create a garbage temporary variable and then turn around and call and then on it. You simply keep walking with the and then and a compose and an and then and a compose. Now clearly the method name could have been better than compose. I'm not too happy with that method name. That just I just don't relate to it as much, but I can understand the benefit of that to nicely say, go through it, nice flow, that can be very useful. So and then simply combines them in that order. Compose combines them in the reverse order, so that's basically what it's doing. That can be pretty powerful operation to perform. So you can see the output of that right here as incremented and doubled, and of course finally you can see that incremented and doubled as well, and then of course doubled and incremented. You can see both of those things working pretty nicely right there. So that's another example of how you can provide some of these nice combinatorial operations very nicely. Well, I'll give you two more examples here that I think are pretty interesting to look at. One is functions on map that can be pretty useful to write some really exciting code, especially if you're doing memoization and things like that. This can come in pretty handy. So let's say for a minute I have a map of integer comma double, and in this case I'm going to say, we'll call this as square root values, and in this I'm going to say new hash map. And here is my hash map of these values. Let's just create it. Now what am I going to do? I'm going to call a method. So I'm going to say output square root values dot, let's say, compute if absent. So rather than calling the put, you can do something like compute if absent. And compute if absent says 4 comma. And in this case, I'm going to say sample colon colon square root. So I'm calling this function compute if absent, and I pass the key 4, but I'm passing a function to it right after that. So let's look at this example. Static, let's say double, and I'm going to say square root int number, and in this case I'm going to simply output square root called for, let's say number, and I'm going to return from this math.square root of the number. So now when I run this code, you can see square root called for 4, and it gave us the result of 2, which is the square root of 4. But here comes the charm. If I were to run this one more time, notice this time around it's not calling that function because that value exists in the map. That's why it's called compute if absent. So if it is already present, it's not going to compute it. It's going to simply return the value back to you. Similarly, there is a compute if present. Now you may wonder why you would need a compute if present, and that is to say if it's already there, I want to change it to a new value. In that case, they give you a by function. They give you the key, they give you the old value, and then you return the new value based on the key and the old value, so you can use a compute if present. There's also another function called compute, which kind of brings that together. It doesn't matter whether it's present or not. It's going to always call it, and then you can compute based on that. So there are a few variations. Very well worth spending some time looking at the map interface to see what new functions they have added in Java 8, and some of them can be pretty concise. I've used this quite a bit in programs, and the code just becomes extremely concise. All that other if and else condition we normally put simply just disappears, and code becomes a lot more concise, easy to work with. And the last thing I want to talk about here is something that can be quite powerful, but we got to be extremely careful about, which is parallel streams. So I'll talk about this for a few minutes before I actually show the example. A parallel stream is a very powerful way to create a number of computations parallelly. It really works on a collection, so the computation of the collection can run in parallel. But there are a few things we have to be very careful before we ever use a parallel stream. Well, the first thing I would say is, if you think you need to use a parallel stream, immediately call for help. That's the very first thing I would recommend. Go talk to a person and say, I've got these thoughts in my mind, I need counseling. So collectively decide whether you want parallel. Just don't turn on parallel arbitrarily. The functions you have in your lambdas, they have to be extremely pure. If you're mutating, it can be really troublesome. You got to be very careful about it. So that is something you got to be very, very careful. The third thing is, your parallel computation has to be really faster than sequential, but that doesn't mean it will be all the time. If your data is really small, or if your task is really fast, you may not get much performance benefit by going parallel, so you have to evaluate and see if there's actually benefit to it. So I've given you enough caution about not to do this until you really, really mean to do it. So having said that, there are quite a few interesting things we can do with this. Let's look at one example to just get a feel for what parallel stream can do for us. So I'm going to start with a list of numbers, let's say these numbers. I'm going to repeat this so we can actually do this computation a few times. So I've got about 20 numbers on my hand. And what I want to do is I want to say numbers.stream, and I'm going to say a filter, and I will call sample, let's say, is even. And then I'm going to say dot map, will say sample double it, and then I'm going to say for each and system dot out and print line. So I'm going to double the even values and print it. Well, let's go ahead and try this out first of all, then we'll come and talk about it. So I'm going to say in this case public, let's say static void boolean, let's say is even. And in this case, I take a number as a parameter. And what am I going to do with this number? I'm going to simply return, let's say number mod 2 is equal to 0. Well, likewise, I'm going to write a double it function. And this is going to return, of course, an integer. And all I'm going to do is return, let's say, number times 2. Well, obviously, in this case, when I run this code, you can see that particular output. But I'm going to do a few things differently. I'm going to output is even, and then I say plus number. Now clearly this is a side effect. You don't want to do this in production code, but this is just an example to show you those functions are being called. But I'm going to then say plus, and we will say in this case thread dot current thread. So you can see in this case, it's going to show you that those computations are being done in the main thread absolutely. So, but then I'm going to come here and say a parallel stream, and you can see right now all those are in the fork join pool thread rather than being in the main thread. So that's what parallel stream did for us. But having said that, let's go ahead and take a look at what's going to happen now in terms of how this is going to work. So I'm going to remove that for a minute. But I'm going to add this into a little thread.sleep, and in this case I'm going to say thread.sleep and give it a second interval. So once I have a sleep function here, so let's go ahead and say in this case I'm delaying it by a second, and obviously when I run this it is going to go through and do one at a time to print the values. If I start with the stream obviously here, I'm going to run this compile. You can see that through the loop once every second or so it is going to print that value out. Is it taking more than a second? Feels that way. So you can see that, of course, because the even numbers are being eliminated, remember, that's why, so it's 1 second per value. So you can see that coming through for every 1 second. Well, that's great so far, but I really want to run them in parallel stream, so I'm going to say parallel stream. Now what's going to happen? Well, it's going to unleash threads on it. So if I go back and run this now, you can see that in this case it's going to be a parallel stream. Still need to spell correctly. So I'm going to run through this here, and you can see in this case it gives us the value. But did you notice something though? Let's actually, to see this, let's go back to the code right now, and here let's go ahead and put output is even plus number, so we can actually see this now. So notice when I run this code this time around, notice that it comes in bursts. So 1 burst, 2 bursts, 3 bursts. So it came in about 4 different bursts if you notice. And the reason it's coming in 4 different bursts is by default the behavior is the parallel stream gives me as many threads in the pool as the number of cores on the machine. And it thinks that my machine has 8 cores, and as a result, it is 8, so it's going through 2 or 3 different bursts in this case to give the result. So the first time it's going to do 8, the second time it's going to do 16, third time it's going to do the remainder of the values. So that's basically what it did. It went through 3 bursts in this case. So that's the default. But what if I don't want the default? I really want a bigger pool size. Well, you can define a bigger pool size by using the JVM option, which is -d, Java util concurrent fork join pool common parallelism. I really like this particular definition because this is finally something longer than my name. I love it. So you can give this definition and say, I want 100 values in the pool size. You can give that. I'm too lazy to type that in, so I wrote myself a little compile option right here. So I'm going to say go in and run compile to, let's say, and you can see in this case it came in one burst, as you can see, rather than two bursts. There you go. And the reason, of course, is I've given 100 threads in the pool. It didn't have to really schedule with the 8 and then wait and then reschedule it. I got a bigger pool on my hand. Well, there's a third option you can do as well, which is a programmatic setting. Remember how you're used to creating executor services? Well, much like that, you can create a fork join pool. And if you create a fork join pool, then whatever you call in the fork join pool will become as part of that. Let's quickly see that actually happening. I'm going to run this, and you can see that come in two bursts. What I'm going to do, though, is I'm going to go back here and say java.util.concurrent.star. And I'm going to say here is our fork join pool, and this is going to be my pool equals new fork join pool, and I'll give it 100 threads in the pool. And now that I'm started that, one of the first things I normally do is to say pool.shutdown, and that way I don't forget to shut it down. Now I'm going to simply say pool.submit, and in this case I'm going to create a little lambda for that pool, and I'm going to move this code into that lambda. So now you can see that the code actually is running, but it's running within that pool created thread. So as a result, it's going to use the pool for running this code rather than running the code outside. So how is this going to work? Let's take a look at this real quick. So I'm going to go back. Oh, we have to wait for this to finish. So that's usually what a wait notification, but I'm going to take an easy route here, just put a sleep for a minute. So this is going to be waiting for this to finish. And of course, that requires me handling exceptions, but not a problem. So we'll take care of that as experts. So throws exception. So let's go ahead and try that little code. So what is that going to do? Well, that's going to use that particular pool we created. So if I go back and run this now, you can see that's still in one burst rather than going through those little values. That's because it was using the pool in which it's using the context pool. So if your thread is in a fork join pool, it uses that pool. If your thread is not in the fork join pool, but if it's the main thread, it uses the system-wide, if you gave an option, or falls back to the default. So that's one of the options it goes through to decide which one to use. So I shared with you a few things that has excited me over time looking through Java. So it makes code concise, makes code easier to write, fewer lines of code to write, fewer mutability, fewer chances of errors. It makes us more productive as well, and we're able to really look around and make use of some of these functions. One of the challenges, though, is the existing functions, existing libraries, existing API, all of them have evolved with newer functions. So something you may have used for 10 years suddenly is brand new all over with all these new added things. So we got to be a bit aware of what's around, and we can pick up and use it, but it's a lot of fun when we start adopting it. Well, that's all I have. I hope you found that useful. Thank you.
understand. איך אקסס דמו ככה? יש לך עכבר? יש עכבר?
יש לי עכבר, תביא, לא, אני, אתה יודע מה, אני אקח עכבר שלי. יש לי עכבר אחר. קודם יש לי USB, למה אתה אומר לי USB? כן, אבל יש לי עכבר אחר, שגם יעזור. It's not displaying for my machine. It's not displaying for me yet. It's not setting it up yet. What? Yes, needs to be HDMI. I'm on. Okay. Okay. Well, we have time. מה קורה פה? מה מבין לו?
לא, רציתי, חיביתי אותך.
מה הפוך? מה זה בין הפוך?
קודם זה כאשר שלך, ואחר כך אתה...
זה היה ככה בהתחלה דבר שלקחתי ממנו.
אתה יודע, אתה רוצה שהיא כל הזמן, זה אתה רוצה לא מה זה, אז עכשיו אתה חייב לדבר. עכשיו משחק זה, אתה יודע, לא תדע בשביל שלך.
גם שלך, גם שלי, אתה שלך, שלי, שלי.
אתה שומע אותך.
בטייטל.
באמת?
למה לא?
אתה שומע מה שקטן.
למה הוא לא מתחבר לקלות לעכבר שלי?
אולי זה במוסך השני.
לא, 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 לא. הוא עכבר, הוא משתולל לי פה.
העכבר שלך במוסך השני. מאוד הייתי להגיד, אבל זה קצת, לא הייתי פה.
מהר מדי, הקשר שלו מהזה לא כל כך טוב. באמת, המיקרופון צריך חדש. למה הוא לא עובד?
מה אתה מחפש?
המניו. עשית לי, בגלל שהורדת לי את הזה, תעביר את זה חזרה, כן, תעביר חזרה, זה עושה בלגן. זה מק, זה לא PC. אוקיי, למה הוא עושה את זה? לא.
Downstairs. What's the subject on this slide? You have plural optimization, but the session is actually singular.
What?
What's the subject line of the actual without plural actual subject?
Yeah. I don't think it's nice. Yeah, too much.
Start a new browser.
This is Chrome. I'm gonna go this one. I'm gonna find
You should sit here. I think I would just go downstairs.
No, I'm going downstairs. You're sitting here. We already discussed this. I discussed it with your manager.
Oh,
It doesn't know how to do the.
I'm not for that.
Doesn't do the. Maybe because the HDMI stuff. It doesn't
No, what does it do?
Look at this. What we're saying here. What we're saying here. It's not. It's
Well, you have
exactly-
extension, or you want to do...
No, it's doing.
You have two screens. You want the one screen?
It's not the. No, it was one screen. But let me see. Yeah, but when I start the presentation mode, it's
Start the
pulling
screen.
up everything. Then it's just
Start
No, no, let me see what I can do here first. Maybe that's something. Yeah, I know. I don't have anything objective. Okay. Now I have to, I made to, but you know, the mouse is less accurate. Now let's try to play this again. Slideshow from start. Swap the screens. Something with PowerPoint. כן. בסדר, אתה מבין שהדביל הזה, למה הוא עושה לי ככה? הבעיה שהמסך שלי הלך לשם, אתה מבין? אני לא יכול לתקן את זה. נו, מה? כן, אבל המסך שלי שם, אני לא יכול לראות אותו. לא יכול לעשות לי כזה. אוקיי. זה מה שהיה קודם, זה היה דבלי.
Do you still have a monitor?
The problem is that
Do you know my calculations on that? You guys are just trying to bring this up?
yeah, but it doesn't go up anymore.
But he wants to do mirrors.
Yeah, but the problem is
Right now, this is a multi-screen.
I don't know what to do now.
Oh, mirror display under
No,
arrangement.
mirror was there. Yeah, mirror.
Where was it?
Yeah. click here,
Arrangement.
and
Yeah.
then mirror.
Oh, yeah, okay.
But still didn't work well for some reason.
Well,
Now try.
If I do a presentation, it's going to the wrong place.
no, it's not showing.
Because it's a presenter mode here. Yeah. Change the way the presentation works to be not use presenter mode. I'm not too familiar with PowerPoint.
Let me just see this for a second.
Slideshow, you know, the middle window is on the slideshow.
It was presenter view.
Let's enable it after doing it. So remove the presenter view.
How?
Well, let's assume that it's not now.
It's not.
Don't set it.
I'm not saying, I'm not
Okay,
looking.
alright. So what happens if you start a presentation now?
I think first of all it didn't do the mirror yet. The mirror didn't catch. Maybe it's just fix the mirror.
Exit PowerPoint.
Let's do this. I can do that also, but let me see what happens. Okay. Looks like it works. Yeah, now it works. Now let's do the slideshow.
Select the top. Alright. You see, it's insisted going in the presenter mode. Yes, it's
Maybe my resolution is too big. Maybe that's the problem.
Could be it.
Probably it remembers my display at home. Not at home, at the office.
Unplug it and do mirror. Oh, you can do mirror when it's unplugged. So every application it's up with the master, right?
Okay. We need to go to. Okay.
So-
Settings. some reason this thing doesn't.
I'm trying to put the slides on the screen, full screen mode, but it wasn't.
You want your presentation to be full screen.
Yeah. But the problem is that it doesn't. Once I move it to full screen, it doesn't display here.
But
It tries, but it doesn't look like it's successful.
Are you trying to mirror it, or are you trying to have this keynote and that be your slides with notes?
No, I don't mind to have just to start the slideshow.
Let's say start slideshow.
Yeah. Wait for start. See, it starts doing something. Flickers there.
Right.
Yeah.
There it is. You got it in keynote.
Yeah, I got it here, but it's not there.
Hey,
Yeah.
put this presentation here. I'll just in case we'll get the backup over there.
I sent it to you by email. Okay.
But I don't have my laptop here.
Okay.
Just see that the actual demo works from here. It will be easier for you. The presentation I can do from there.
Mirrored.
It was mirroring. Look at this.
Well, no, that's not mirrored. Well, yeah, it is actually. You're right. It is.
Copy it over there. Let me back up. 5 more minutes.
Try hitting.
Just a second. You want
Okay,
to
you
copy
want it.
something, so you can work on something in the meantime. You know what? I know what I should do. You know what? That's something else I could do. I need to close a few. Maybe I'll close these. Maybe that's what's confusing me. Let's try this. One try and see if this would work. Slideshow. Yep.
Okay.
It just doesn't know how to
You
deal
had,
with
you had
virtual
another
screens.
program open, right?
No. It's virtual screens. It doesn't know how to deal with virtual screens.
Oh, okay. I see.
Now Avi can get his
You want
backup.
Yeah, your cancel the mirror for the demo.
Did you want to click here as well?
There's one. What?
Did you want to click here?
Oh, I have this. Oh, how do you do it?
We just plug it right into there.
Oh, okay. You know what? Why not? Yeah, why not? What's the problem? Oh, okay. I don't care. Okay, you want it? The mirror is the same screen. It's not non-mirror, it's mirror. It is mirror. It's just PowerPoint does that.
When you get budget ready, for the
Know what happened now? And the clicker is okay. Sure. Thank you. Okay, I don't know. You want to do?
I'll just move this further back.
No, I want to read it. Yeah, I want to read this.
If you want to read it, I can put it in.
Yeah, sure. You're right. You're right. I need a telephone.
Selfie stick.
I want to use. No. Audio? No, it's gonna. I don't think it's gonna hold. Oh, this thing you're saying? Oh. Who is my phone? I think it's because he has the same thing in this session. Same reason. They said the name, they left. Should we go? Yeah, that too. No, my phone is on. Okay, okay. We should be starting. Okay. Good afternoon, everybody. Happy to see such a crowd here. It's late Thursday. I'm hoping everybody had fun last night with the Elton John and everything. So I'm Michael Abrahamov. I'm the Senior Director of Development for Java Diagnostics at Oracle. Then with me I have Avi Huber, who's the Senior Director of Product Management for several items, but one of them is JVM Diagnostics. And then May is the architect for the product for the most part. And she's going to fix things when I break them. So, so we're here today to talk about what happens really after you finished and you were successful and you managed to get your code running in production, and then things really start to be more interesting. You do whatever you can do in development and obviously in testing and production, but before production, but things really show up in production differently. There's a safe harbor statement, as you've seen so much, so I don't know if you want to read it, but so okay, so what is the workload that we talk about here? So in terms of dictionary.com, workload is something that is defined based on something that a machine, employee, a group of employees can do, expected to do in a reasonable way. When it comes to Java and to our world, really we're talking more about application that needs to run well with the resources, the machine that it has, and the different types of things that you throw at it. And you expect it to really do well. But the truth is that it's kind of hard to define ahead of time what the workload is going to look like. You know what you implement, some things get invoked in testing, some things get invoked in production, but for a very long time you don't see them at all, and then at some point they start shooting up because somebody started using a module you didn't see them doing. So really the workload is very diverse, and it's throwing, sometimes it's throwing some curveballs at us, and it's kind of hard to just say, okay, let me try to reproduce something that you complained about that happened last night. Let me try to reproduce it in my own testing and get to understand what's going on in my own dark room. So there's a lot of stuff that we're seeing in production. Our customers are telling us that they have issues with. So the ones that we are usually, the kind of conflict that we usually see between developers and the folks in operations is there's really very little patience in ops for a developer to go and meddle with things. I mean, they need to really keep the things up running. They have their own requirements for compliance, for everything is audited. Allegedly, of course, the things that they do sometimes are not audited. They don't make changes and things fall apart. But then, you kind of track these things. But they are very careful about who can get where. And the truth is that the world that you know in development, where you can actually hook a debugger or you even go on a host and play around with it, that world just doesn't exist in production. Some customers would have forms that you have to fill. Some production managers will want you to fill some forms, and they get approval, and you get a downtime to play with something. It's kind of difficult. And of course, we really want to deal with, we're going to get to things. That's not the slide that I was supposed to be seeing. think it's weird here. Okay. Yeah, you may see things a little bit out of order. Sorry. Okay, so why proactive? So what are we talking about proactive here? For proactive, it's a little bit different of an approach than what we sometimes see the ops doing. I mean, in ops, you see, typically what you see is they're more reactive. They're more driven by problems. Something doesn't meet some KPI, some service level that they are contracted to deliver on. And that's what they do in many times, that's what they monitor and that's what they deal with. But we've seen in the past that they still have, in production, they still do things that are more proactive. DBAs, for example, database administrators, they don't just wait for somebody to complain that SQL is, or a page is executing slow or things like that. They have the tools to look at their system as a whole, to look at what it's processing, the workload, they look at where it's spending its time. Not necessarily that they know that somebody is going to complain about this, but if they look at a SQL statement that is executing for too long or consuming too many resources, they're just going to chase down the person who wrote it and going to say, you got to fix this. I don't know who's going to complain about it, but not in my database. We want to get in a similar fashion to do the same thing in Java. We don't want to wait till somebody calls at night that something is broken. We need to make sure that we understand how our application behaves all the time, monitor it all the time, and see if things are doing egregious things, low contentious that shouldn't be there. You know, they might not be a big issue in a small scale, but if you have a higher load, all of a sudden that thing becomes completely irresponsive. So we want to be able to do all of these things to reduce outages and to be more, really more efficient about our resources, because you can't just waste these things. It's not just about the money of the hardware. You throw more hardware at something, what comes with it is also data center capacity, ventilation, power. You can't just throw hardware at everything. So that's another thing that to bear in mind. So really, so what is the mission in production that is kind of we need to pay attention to is their role is basically keep the system running. Running, that's it. It's always service availability, and service availability is not just up-down. It's whatever you define service. And they measure it by, I mean, this is a simplified formula. You can get and see a sigma formula that talks about and breaks it to multiple other things. But at the end, it's about how much time the system is operating between failures, divided by the time, including failures, and the time that it takes to recover from a failure, basically. So what developers, really what developers want to make sure is that the code is operating at quality. So, you know, what we want to do is to make sure that we don't have failures. So that requires really investigating sometimes things, and maybe we are willing to pay some price of looking at a system that it's hurting. You know, I don't mind if somebody is telling me I have a huge GC overhead right now, and you know, the JVM is at full capacity and GC is acting up. I would want to get a heap dump and analyze it, because I don't want it to get to the same state again in the future. What the ops would want to do is they would want to just bounce the JVM as soon as they can. They're not going to wait for minutes to get the heap dump that you want. That's an example. Or even just any stuck threads or anything that you see. They're not going to wait for it. They don't have the budget for it. Because if you look at 5 nines, I don't know if anybody here, do you know what it means, 5 nines? How many minutes can you be in a year? How many minutes, hours you could be down if you want to support 5 nines? Anybody want to guess? 5 minutes. 5 minutes in a year in total. That's the thing. So if I need to dump a heap and it takes a minute, you took a minute out of my downtime, I'm already in trouble, because that's how you want me to give you the heap dump. So that's really the story. So that's why we want to be proactive. But to be proactive, you really still need to have access. You still need.
Want to go back to the types of the applications?
Oh yeah, yes, correct. Yeah. So I actually, before that, I was kind of, it's a mixed crowd. I don't know if people would volunteer and raise their hands and tell us a little bit about what kind of things they do, especially as it pertains to production, the type of issues that they deal with. I'd be interested to hear. Any first volunteer?
A few slides back, you
Yeah,
had
I know.
types.
Yeah, because we talked about this, and I think one of my slides was a bit off of what I thought. I don't know what happened with it. Anyway, but anybody volunteering some? Oh, good. Heap exhaustion. Heap exhaustion, yeah. And then usually what? It's inevitable out of memory or worse?
Fortunately, just that so far.
Yeah, because it's actually, yeah, so the gentleman at the back was talking about heap exhaustion. The truth is, it's not the worst you can have. If the JVM actually crashes, it's not bad usually, because usually it would bounce again. Most of the servers that you have would have some facility, some watchdog, some node manager, something that would bounce it again, but sometimes that's not what happens really. It just gets into minutes, possibly even hours, where the GC is just thrashing. And then that's really bad. You know, I see people, nodding about that. So anything else? I imagine some of you do web services, web applications. Any applications that are not web applications in production? Yeah. Yeah, that's the other thing that you reminded me, basically. We see these things as on web containers as well. What happens is the same thing that we talked about before, like a long pause that happened. Usually, most developers don't really plan for that. And what happens is you get things queued up. You come back from this long GC pause, but all the requests that you were supposed to be processing are backlogged. Those requests fire in to the thread pool, and they bring up all the threads, and you're already stressed for memory. So that's, things get compounded. And if you're lucky, it crashes. That's your best case scenario. So the 5 minutes that you have to work with, you might be able to work with that. Okay, we'll move on. So really what we want is when we are in production and we want to do the diagnostics and being proactive, we really need to have access. But access, like as we discussed, I don't know, I wonder if anybody else has a better experience with getting access to machines, to hosts in production. Anybody here usually gets on hosts in production? Oh, you do? How do you get that? What? Oh, okay. Okay, so I should be careful about what I say about sysadmins, huh? Yeah. Yeah. Anybody? Okay.
I'm actually a developer, but I also have access to production because we don't have that much of a staff. But we're heavily monitored. So I have to restart.
Yeah. So you also sometimes you fight with yourself sometimes. Yeah.
I have a sense that the access has a lot to do with the scale of the deployment.
Yes,
The
of course.
larger scale of a production environment, it is the harder it is to grant access to people.
Yeah. So in Oracle, we deal with the Oracle Public Cloud assets, and there, really, we don't get access to. If we get any access, it's supervised access. And of course, you need to schedule a meeting, and it's not when something really bad happened. So you can't really do anything. And you need to know, again, for the scale that we talked about here, the gentleman here, obviously you know exactly where everything is running. When you look on a bigger scale, you need to know where the services are running. It's not that easy also. So those are the challenges that we're seeing. So what we are looking for when we at Oracle, when we implemented our own solution, which is not the only thing that we think is possible to do, what we're looking is really to get access, not supervised, but controlled access and audited access to the systems So you can get to the application, understand the mapping, the service directory, understanding, being able to do things online when something happens right now, but also historically go back and see things and be able to look at things when if they happened in the past, or just analyze data if nothing happened. Just be able to look at data and figure out if this is how you want the application to execute. The other thing that we do is we listen to critical events in the JVM. And I think even if you don't use Oracle, if you have your small shop, you do your own things, you really have to sometimes, you need to factor into your code some means to deal with production issues. You have to at least instrument it in a way that you know, I took this this is where I'm taking the workload that I'm supposed to be processing. Let me instrument it some way. This is where I finish things. You got to do some of these things, otherwise you'll be left with, in production, you would not have a debugger, and logs will not do you that great for performance usually. They would be good for logic issues sometimes, but you'll need data and you need to enrich it to be able to get the data that you need. You could do, we will talk later about JStack. You can look at JStack, but JStack is not going to be good enough if you don't enrich it with some context. Okay, moving on. So what do you do in pre-production? Okay, actually this is maybe a good question for the crowd. What do you do before production? Of course, in production you can't really do stuff, but you do run some load in production. You have performance, scalability. What do you do there? What are you using to profile, optimize your applications? JMeter. Okay, just to run the load. And to profile?
I forgot the name, what used to be JRock.
Oh, JRock mission control. Okay, that's good. New Relic? How do you profile with that? It shows you what?
Shows how long your request takes to serve, what exactly it takes, how much your application spends in DB, how much your application spends in external calls. It is not, I would say, a complete report you're getting from QA, but at least you can get some.
Well, you know your response times, but you get that also from JMeter. If you're running JMeter, you know your timing. JMeter gives you every statistic. It doesn't give you the breakdown in terms of. Yeah, I know. Yeah.
Relic has a profile button and it's snapshot kind of a thing, sampling probably.
Okay.
But it'll show you where you're spending your time.
So you can selectively decide to get stack traces so it does sampling similar to JProf, like HProf, or yeah. Okay.
Well, I did read the batch because instead of thousands of requests, I use batch data. So we put a server, the file we used to have mission control, but after some time, people didn't understand too much more in the interface, so we established that.
Oh, you established it.
Yeah, because it's very, nobody understood the licensing.
Ah.
But Spanish people install NetBeans has been go for.
NetBeans? Okay, yeah. So actually many people use profilers to some extent. Of course, they have some limitations, but you have to do this in sampling. You have to do sampling because if you enable the profilers to really the full feature set, you would be messing with the test as well. You can't load the JVM if you're not sampling. You have to do just sampling and be careful about what you instrument. But the problem with that is, again, you need to really understand the context of what you're sampling. And if you look at any profilers, they don't really know. They know the JVM, they don't understand the context of the application. And I think some of you, even mission control is not always, it doesn't always figure out the context. If you have If you're running in WebLogic, you have a good context of what's going on, but if you run on a JVM with some other application container, mission control won't necessarily know that you're running requests even, on what the requests are in your code. So you're going to be missing some of this. You know that your hot methods are going to be, AY, AAX, ABC, or whatever, but you won't really know truly if those are methods that matter. So what people do, and this is something that if you're using these things, what they do is sometimes again they're filtering out. They develop some through some configuration files. They develop some means to filter out threads that are really not executing a lot of any workload. We actually call them idle threads that are waiting for workload instead of threads that are processing workload. Okay, JStack. Somebody mentioned here JMC as well. These are the things that we've seen. GC logs and JMap. Some of these things you can do, not necessarily in production. Even JMC, in a small site, you can get with JMC. I think in a bigger site where things are controlled, you suffer from the same situation. GC logs you can collect if you enable them, but you have to enable them either all the time or hope that the problem will happen again. Okay, I wanted to just show a little bit what it looks like. So maybe if some of you don't know how to. How it looks like when you do JStack in a real situation.
Can everybody hear?
Yeah, I'm not. So if we look at
Increase the font.
oh yeah, okay, yeah, I see that. Sorry. Yeah, if you are complaining about it, I can imagine what others would say. But fortunately, I don't think I can scale this. This is a Mac. But let me open another screen. Oh, this is also small. Oh, you know what? I'll do something else. Oh, good for me. Oh, it's here also. Sorry. Displays. Bigger. But probably people at the end won't see it. But I don't think we need to look at all of it, but I just wanted to show what's important to show is how many threads you actually have when you do JStack. Is it not readable, right? Okay, maybe we should skip this. Yeah, in the terminal I can, but okay, let me do it from the mouse. Zoom in. Mouse is flaky. No, I'm good.
Not important right now.
Yeah.
Say what you see.
Now it's visible, sort of? Okay, let's do this for a second. Oh, sorry. Yeah, sorry, this is C stuff.
We can still get stuff on PStack. It's just different.
Yeah, I don't know, anybody here knows what pstack is? Used it? good. Yeah. So let's do, I'll do more because there's no sense in doing all the way. So, okay, so this is a server, a WebLogic server. Similar things you'll see in many frameworks. It's going to be very shocking if you know, if you haven't seen it, but okay, I'll do something that will see how many threads we have. This is way too many, but so we have, I think it's, NID equals something. Okay, I'll do
How
this.
many people are familiar with JStack? Okay, more than half.
Yeah, and then we'll do WC-L. Okay, so this one actually right now doesn't have that many threads. Usually you would see hundreds and hundreds of threads. This is just 137. But the important thing is most of them are doing nothing. So that's part of the issue. The other thing that you have is sometimes is that you would want to know, you know, I'll do a grep. Okay. So if you look at JStack, what it provides you, it actually looks at the threads and tells you some threads are blocked, some threads are timed or other things, and some are runnable, sleep. Some of them sleep, some of them runnable. The problem with that is even that is kind of a bit flaky. Runnable in, anybody knows what runnable means in Java when you do thread dump? You? It means that it's in the run queue? What does it mean that it has the potential to? Well, the main thing is actually based on what the Java implementation does. Runnable means that really Java, it's almost like a catch-all. Basically, in Java, we just don't know what it's going to do. We know it's not sleeping. We know it's not blocked. It could be native. And then obviously we don't know, even if it does a poll or select or something, from our standpoint, it's runnable. And it could be really runnable. It could be in the run queue. So these are the challenges. You do JStack, you don't know we would see the threads. You won't know how the threads are associated with requests that you're executing. But you have to use it sometimes if you're in production. You have to get thread dumps from the customer. Right? I mean, we many times find that we have to ask the symptom-bearing individual to give us either JMap or JStack or things like that because we don't have access to it. So an email back and forth between the developer and the victim, and we ask the victim to help us by giving us JStack. Anyway. So I won't spend too much time on this specific thing because I think we'll be, it's going to be challenging with the, my skills with the screen here. Okay, so these are the things that, where's this? Okay, good. Okay. So what do we really want to have for proactive? We talked about resources, we talked about workload. The important thing is really to understand the relationship between those two things. We need to really understand how the resources are affecting us, how much time we spend on each resource, and resources. And this is similar to what we do in the database. So there's a lot of history behind this. We want to know how much time we're spending on CPU, runnable, or in run queue, memory, I/O, what is blocking us, external resources like database, RMI, other calls, and we need to look at these. And what we do in the model that we look at each thread and we say, what is that thread executing on? What resource is it relying on right now? And we categorize the thread dumps that you saw. First of all, the first thing that we want to do is to throw away all the threads that are not doing workload. So we need to identify that they are actually doing workload. Second thing that we do is we just break it by these categories, these types of resources. Now, the second section here is talking about, okay, so now I know that I'm I'm waiting on CPU, or I'm waiting on I/O, or network. That's all cool, but who's actually consuming these resources? So for the same type of workload, you really want to know how much memory allocations it's doing, because that affects everybody when you allocate memory. Not necessarily retaining, but at least allocating. You want to know how much CPU you're consuming. If you track this over time, between versions of applications, same like in the database, you can figure out that the same request a version ago was doing 100 milliseconds of CPU, and now it's doing 500 milliseconds. That is not right to do 5x all of a sudden in CPU. Something might be going bad here. So these are the things that...
it's interesting to get a resource usage by requests, right?
Yeah. So based on what we call... So we look at these things, even people that don't do necessarily web requests, we model things in terms of requests to just normalize on one name for this workload. So workload is comprised of many types of requests. We call the different things that you can actually observe, we call those things requests. So it's a web request, but it could also be a job that is a request. So as long as you know what is the start and end of this thing, that to us is a request. So some things that I think I would recommend here for people that just want to use their own home, they just want to enrich their thread dumps. I would recommend to do a few things. If you instrument your code so that you could actually be more effective with thread dumps, one of the things you can do is you can rename the threads to define what the thread is doing. We're doing it in our code when we rename the threads. WebLogic does that as well. So if you take a workload, you're executing a job, you can give the name of the job to the thread, and when you finish the job, you can remove the name. You can bring it back to pull thread number 1. You can also decorate the name of the thread with the thread ID. You don't have to because you already have it with the JStack, but it's going to make things a little bit easier, especially if you add to it the current time, because current time and thread ID would give you uniqueness of the execution of the thread. It's almost like an execution ID of the workload that you are executing. When you have those and you get thread dumps, the thread dumps would look all of a sudden a lot better to you. You know which threads are actually executing. You can actually grep by these things, and you can start also putting them in database that you make on your own or in Excel, and mess with these things and figure out what things are. It's not easy still, and you're going to still be missing some things, but I think that's an easy thing to do to get better thread dumps. Otherwise, you'll see the thread dump that I just showed you, and that's not going to be extremely useful. What we do at Oracle is we do things that go beyond that, because what we do is a whole interaction with, which is what I want to demo, is how we look at things from our standpoint. Okay, maybe I'll go back to better resolution. I think we can do better resolution for this. Actually, you know what? It's fine. We can do with this. Oop, that's not what I meant to do. Yeah, no, not necessarily. Okay, so what you're seeing here is what I talked about before. We mark every thread. First of all, in this, what you see here, we do essentially a few things. We instrument code that wasn't instrumented before. We instrument it with the events that relate to taking workload and processing it and going to other systems or other important things to obtain some resources that are meaningful enough. Let's say if you go to database or you go outside to HTTP, we track those things. So we kind of figure out what events are going on, but we are not collecting these all the time because that's going to be expensive under heavy load for production. We're just tracking it but the way we actually get access to the data is by sampling. So we constantly sample and sample and sample. And what you see here is our sampling. The height of this is the number of threads for this application, and the colors, you can read it. I kept it big. Some of you could read. The bluish stuff is I/O. The red is CPU, and CPU is usually good, actually, but we kept it red. Database is threads that are doing stuff in database. And we just aggregated across as many JVMs as you may want to monitor. It's a cluster or multiple cluster or the whole data center. You aggregate things, and you can see a good feel of what your workload looks like in terms of resources. And you can detect, even here, I think people could see that there's a shift in the behavior in this specific thing. We see that there was a period in time that there was contention. Blue is contention. We don't know yet from this, because it's multiple JVMs, the table at the bottom, we don't know yet which of the JVMs has it, caused it, but we know that there is contention. Yes, sorry. Oh, there's one JVM here. Yeah, because okay, let me add the other one also. I already filtered out a JVM that, so okay, May corrected me. So actually, this specific site only has 2 JVMs. And you would see here the cumulative count of the processing threads based on what type of resource they're spending their time at the moment of the sampling. That gives you a good feel for what is your bottleneck, what is your resources that are being slowing your application, because that's where the threads are spending their time. So around here, we see a lot of database also, but we also see I/O. We see a period of time that is logs. Now, nobody has to complain about anything here. We are saying proactive. It's not about somebody saying that something is slow. But me looking at a chart like this, usually what would catch my eye is, why am I logging a lot? And what would happen if I'll see monstrous load? What would happen then if I have these logs? So how do I figure out who's responsible for those logs? So if I have multiple JVMs, this is not many though, but if I go and zoom into the area where this log happened, I can actually see the JVM that is the culprit. There's one JVM that is doing a lot of database. That's actually the JVM that we are interacting with right now. The JVM below it is the JVM of the sample that actually you can see that it's spending some time in logs, sometimes in I/O, sometimes in CPU, and there's a little bit of database. What we can do is also look at what, if you look at what we show in there is how much time the JVM is really active. What we call is JVM time. It could be more than the wall clock time, because you are running multi-threaded, multi-core. It's more than the wall clock time. But this gives you a good understanding of how much the JVM is really active, because these are only active threads. So for this JVM is active about 20 minutes. I think about 20 minutes out of the time selected, and the selected time is 7 minutes. So that's pretty active. You can see high-level stuff immediately. And that's why you need to aggregate things, and you need to get to MBeans sometimes and things like that. And we also show the GC overhead. GC overhead, I don't know if people here, anybody familiar with the notion of GC overhead? Okay. Oh, well, okay. So, okay, so GC overhead is really more of a calculated metric. The way we do it is we look at the GC processing time, and we divide it by the local time, the wall clock time, and because you know that the GC, the time that we're measuring is GC that is actually pausing, then you know that this is the overhead based on what you're supposed to be processing. This is stuff that you couldn't do in that time because GC was giving you that overhead. So that's the GC overhead, and those numbers, ideally you don't want to see them above 5%. Above 5%, you'll see already some impact. We put thresholds usually around 5, and then I think 10, or maybe 7 and 12, or something like that. But it's really needs to be really low. What we can do here is I'll go back, and again, this is the data process. After we've done, yeah, sorry, yeah. It's the number of threads that are active. So every time that we sample the thread that is active, we count it as one sample. And we sample, in this thing, we are doing sampling every 2 seconds. We can do it in various, it's something that people could choose how often. Out of the box, we do every 2 seconds. And we count every 2 seconds like that we see a thread, we count it as JVM time. So if the thread is active, let's say you said we were running, we got 10 samples, and we saw 10 threads, it would be 100 seconds. Now, it could be that we had these 10 samples, and later there was no active threads. We still sampled, there were no active threads. It could be for an hour, you didn't have any active threads, so it's still going to be those 100 seconds for that hour. But then you know that it's idle for the other time. And the height is really also something you can look at in terms of thread samples, 10 seconds. So I'm going to go and do some, okay, actually one thing that we could do is also, even at this level, we can look at what requests are executing at the time. So even from this standpoint, even at the level of multiple JVMs, I think I don't have to even say, but you would see that you can see which request is really doing the locking, the contention. It's not everything that is having a contention, right? So you can see here, because it's decorated, because we know what the workload is, it's not just JStack, we know which request is doing what. And here we see also, that's the thing that it's not gonna be that easy to do, but still doable, is even if you build your own thing, you still want to know how much CPU the request was taking, which is things that we're showing here. And you can also count the allocations. There are counters in the JVM, in the platform beam, that allow you to know how much you allocated. So you can, in any given point, each thread tracks how much allocation, how much memory it allocated. So this is really cool to be able to look at the allocation, because it's not always that the allocation is a big deal. The allocation sometimes is just a good measure of activity. Same like you look at CPU. If you're doing a network read, it's not very easy to know if the read is just blocking for traffic, waiting for traffic, or really you are reading. You do a JStack, you'll see something in socket read. It could be just idle, waiting for something. But it could be actually reading. If you actually can track how much memory was allocated, you would know that it's actually reading and not just waiting to read. Right, so you can use it that way. Yeah. No, not open source. No. JMC, not open source also. You can calculate it actually from GC logs also. You can calculate the GC overhead from GC logs. That's probably the best you could do. But so the thing is, okay, so it depends on the crowd. The tool that you're seeing here is a tool that usually is available in productions. In big productions, they're using this. It's all a matter that sometimes they don't know that they can, that the developers can take advantage of it. So it's not that, obviously you would prefer to do things in, even some of these things you want to do even in your own environments, so not just relying on admins in production. I think there are ways to deal with that also. Yeah, we can talk about that later, but I just want to, just the concept. Let's go over the concepts first, and then figure out what is the other, yeah.
In a dependency injection-based application such as Spring, can the same concept apply? Like we can name the threads. How do we control the?
Okay, the name the thread is a notion that I kind of suggested that you would do if you want to do it, on your own. You want to do some things. We don't name the threads really. What we do is we catch the actual invocations of, for example, of a servlet or any similar things that are executing in the JVM, and we know how to catch. Basically, some of it is based on some bytecode, but even without bytecode, we know how to find the object that defines the workload. and then we use that as the name of the request. So even in Spring or in other types of infrastructures, we grab the whatever defines the workload. And in situations where we don't have that, what we do sometimes is just based on the stack of the execution, we define what is the user last method before. It's not the last. The first method that out of the framework became a method that actually is executing the workload. So we may not, in those situations, we may not have the exact request name that you expect to see. But for example, if you were doing this, if we didn't know anything about JSP, what we would do with this method, we would get to at least the name of the compiled Java class that executes the JSP. We wouldn't know that it's a JSP, but you would know that this is the method that executed the JSP. What we would also be missing is we wouldn't know when it started exactly. But for example, the top chart, you would know without needing anything. You would know where you're spending in terms of specific requests, foo underscore JSP, blah, whatever. You would know that it's consuming mostly I/O, because we would know that every sample that we took is categorized by that artifact in the stack. Any other questions? Okay. So, how are we doing on time?
15 more minutes.
Okay, what other things that we do is, so let's look at what we do in terms of other resources. Okay, actually, not this. So we went to requests, but request is not the only thing. We talked before about instances of request. It's not just that you want to look at request as one cloud of things. Sometimes some of the requests, so we show averages. You can see here that we show the averages, we show the max duration, but it's never going to tell you enough to deal with one sporadic slowness. You really want to go a little bit better into the instances, which is what I told you before, why I would recommend that you do. Sometimes what you would want to do is to decorate the threads with the current time that you started taking the workload. So here you go, at Oracle, we call these instances ECID, Execution Context IDs. I don't know if you heard of those things. And they go at Oracle all the way to the database in the Oracle stack. So if you're using most of the Oracle stack, would have that, and you could tell even what SQL was executing in the database based on that execution ID and what it was doing at the time. So here we see the instances, and you can see per instance the same thing that we showed in aggregate. I can show per instance that the instance took point, the top one, for example, is 200th of milliseconds. Of seconds, sorry, it's 200, it's 20 milliseconds, right? In terms of CPU. In terms of allocation, it allocated 6.42 megabytes for that instance. Obviously, it didn't do that much because it was mostly locked. And you even see that the I/O wasn't that dramatic here for the duration, because this request took 14 seconds, and it really didn't do that much. We can see, the other thing is, let's look at how to what level we can go on this. We can actually go to the level of, we can go to, the other thing is, because this is an integrated system, you can even go to the logs on this specific instance. You can see the log files that this instance emitted if you want to. I wouldn't really focus on that, but I'm going to show the call tree, for example. What happened here?
Is the ECID part of the JVM? Is something in the JVM, or is it something that can appear at runtime, or is that ECID?
It's part of Fusion middleware.
It's part of the Fusion middleware. Fusion middleware is the Oracle stack for, I would say, J2E, the J2E stack at Oracle, and it's instrumented as part of it. So if you get WebLogic, and you enable that feature, it tracks everything for you. And if you have SOA or OSB, all that framework is instrumented. Some of Oracle applications that are built on that infrastructure are also instrumented. So if you end up using them and even integrating with them in your solutions, you can take advantage of that. Okay, so this is, the cool thing about this is now that we can actually do, this is obvious, right? We could look at this request, this specific request, and look at it and see the stack traces of execution. But actually, the stack traces that we collect, we always collect them. And for all the requests. So the notion of looking at the stack trace, it's all good to see with one instance, but you can also pick multiple instances and look at the stack trace, the aggregated stack trace. It's basically contextual profiling. You're not just looking at a cloud of everything that happened in the JVM. You can pick specific requests out of the stream because they're the slowest, for example. You can pick them and look at them in the, as an aggregate stack, as a profiling stack, and you can see the call tree. And you can go and open it like any profiler. Developers, I'm sure you've seen these things. You've seen a profiler. You can open this more, zoom in on the heavy stuff, and and on and on. And you see the line of code. You see the methods. You see the line of code. The file name. You see all of that. And this comes from production. And you don't need to be there when it happens.
There's a question?
Yeah, questions? Because we're doing sampling, it's kind of even hard to give a number because it's not integer. Basically you can't notice the time. And it's controlled even. If you have any concerns, you can, the cool thing about doing sampling is that you can play around with the frequency. If you say, okay, you know what, I don't mind, I don't see any impact, maybe I want to have a higher frequency of sampling. I don't like the 2 seconds out of the box. I want to do every half a second I want to sample. The gotcha about this is that this is really for high production environment. So what you'll find yourself at some point is if you increase your frequencies that you need a huge database to store the data. We're bringing the data. We're not keeping it in the JVM.
Michael, I think it's useful to add here that the point of the overhead, because of the sampling, is the overhead doesn't depend on the actual load of the system. So if you are monitoring and you have the normal low load that we have, now you suddenly have higher load. And in many tools, once you have high load, this is when your application is in problem. This is when you want to bring up your monitoring, but your monitoring now have increasing overhead because there's more load on the system. But because we are sampling, it's the same sample all the time. The overhead, the minimum overhead that we have is the minimum overhead is exactly the same regardless if we have a 10 transactions per second or 1,000 transactions per second. So it doesn't affect the actual what you're monitoring. Yeah,
I'll actually emphasize on this a little bit more because one important thing is to notice is to understand here, when you do things like executing based on event tracing, like bytecode injection. People here mentioned like New Relic. They're not alone. There are other people who do that. They actually execute their work on the execution thread. They have no choice. They have their bytecode. It's as if you wrote the code to do the instrumentation. They just do it in bytecode, which is a cool thing that you could do this. We also use this here as well to get some things, but we were very conscious about still keeping our sampling as the main means to get the richness of the data. Because really, as Avi was saying, and one of the things that we did is we did introduce some bytecode because we can't track the resources if we don't know exactly when something started or when something ended. If we just sample, we won't know. So what we did is we introduced some bytecode. For example, on a servlet start, we have some small code that runs in there, and when the sample ends, we have a little bit of code that measures what we want at the end. But we're not aggregating any of this. We're not even getting the name of the request at that point. We're not doing almost anything at that point beyond the absolute necessary that we have to do in the context of the thread. We respect the context and the integrity of the thread so we don't screw up anything. That's a funny story, though, because we had our PSR, even with all of that I was talking about, we had our PSR doing testing, and they, you know, it's not PSR really, it's quality assurance, and they were lacking on methodology, but they kind of blew up with some concerns about performance. They were saying, oh, it's like 40% impact, and we know what we are doing. So obviously they were wrong, and it was very easy to prove it, but at the same time I had the person that was doing this code, he was not trusting them. He said, okay, I'm going to write my own application, and I'll see what the impact is. And we measured everything. So he had his own application that goes all the way to the database, does a select from dual, which is less than a milli. The whole request that is traversing only code that we are instrumenting took less than a millisecond, back and forth to the browser. And he was running it under load, hundreds in a second, the same request. And then he's telling me, Michael, I don't know, I have overhead of 20%. I said, what? 20%? What are you running? So he explained, I run a request that is 1 millisecond and a high load, and you know, obviously, so I said, okay, let's measure how much time you take in the minute code that you execute, how much time you take in terms of really wall clock. So he ended up finding that he was taking about 200 microseconds to process his stuff. Now he was doing nothing. I'm not kidding. You can't do less than that. We found that, actually I'm lying, you could do a little less than that, which is he was creating a unique identifier for each of these requests, the thing that you see here, the ECID, that was taking 50 microseconds. That's not nothing if you care about 200 microseconds. So we optimized that. He, by the way, found these issues with this tool. It's funny, even though it's such a small thing, he ran it and we checked it in this is called JVMD. We ran it in this, and the same thing that you see here with the, you know, where you're spending the time and the distribution based on sampling, he found these issues themselves. He tried mission control, but mission control, again, it's a pretty big tool and takes a lot of events, and it's kind of sometimes difficult. You really need to understand how to throw away the noise out of the tool. The tool is amazing, and we use it here, and this, by the way, allows you to get JFRs from remote JVMs. You don't need to be on the host. If you have a site that is using Enterprise Manager, you can go, as a user, you can get your own user on that. You can go from your browser, you can go and say, okay, I want to dump this JFR, I want to start a new recording. You can do all of it from here. You can download it, and if you have mission control on your PC, it would open the file and show it. Yeah, we have, well, that's okay. I think in terms of demos, yeah, we're running out of time in terms of that, but we can definitely answer questions. Yeah?
Are you also using Java Flight Recorder?
We are using Java Flight Recorder in the sense that we do a few things with it. First of all, we enable it. We enable access to it in production. You will find that in big deployments, it's very hard to get access to Java Flight Recorder. This allows us all the JVMs that we know about, you know, the domains, the pools, the data centers, all of that is managed like this. We have, because we have an agent on those JVMs, we allow you to start recordings and dump JFRs. We're not using the JFR in this UI. Well, what we do with JFR, besides just dumping it and getting access to it, is we create reports out of it. And May is probably trying to navigate there. No?
Yeah.
Okay, good. Yeah. So we have reports that we parse the JFR files, and we have right now 2 reports, but we would enrich them. One of them is a report that talks about GC. If you have a GC pressure like you may have, we can tell you what was affected by that GC, and also what was allocating memory. Because the cool thing about what JFR can do that we can't do and nobody can do without impact is, even they have impact on this, sorry, I'll correct myself, but it's not a material impact. They can catch the stack traces of the allocations when they happen. So if you have something that goes out of whack and allocating memory and causing the GC to trash, this is extremely useful to do, to dump the JFR file and look at the allocations.
I want to add that since we're talking about proactive optimization, we support threshold-based actions like dumping JFR snapshots as well as heap snapshots. I think many people are interested in memory diagnostics, out of memory exception, or the JVM runs out of memory. And you can proactively take some heap snapshots and we can compare and give you the root cause of the memory issue. So, this is another usage of for the proactive optimization.
I think we got signal that we have. Excuse me? Are we the last or there's somebody waiting?
No, someone's waiting.
Oh, okay.
All right.
Okay.
Thank you, Michael.
Okay, thank you.
Thank you.
Thank you, guys.
Here or the door.
right. Hello. Yeah, we're starting. First of all, thank you all for coming. I know it's the last session of JavaOne. As an attendee, not for the first time I've been to last sessions at JavaOne. I was always thinking like, well, I'm glad that's not me. And this year, for the first time, it's me, and it's actually not so bad. Look how many shown up. All right, brilliant. Today I'm going to talk in my last talk about the Java memory model. And I guess most of you have a basic idea of what the Java memory model is. But today I'll try to walk through it and make it a bit more accessible. Because I'll be honest with you, the Java memory model isn't easy. I think it's actually, for me at least, I think it's the hardest part of Java, the programming language. To understand the memory model took me years. And I still have moments where I feel like, okay, am I 100% sure about that? And the thing is, the Java memory model, if you read through it, it reads like a PhD thesis. And that's not coincidentally. The Java memory model was developed as a PhD thesis. And if you read the original thesis, you can actually tell that it's basically a copy-pasted into the JLS. So it's very formal. It's defining the Java memory model in forms of orderings, and today I'll try to avoid that. I don't want to go through formalisms. I want to look at the practical side of what the Java memory model does for us and how we can basically apply this knowledge. Because understanding the memory model is important. I can tell you so much already, and I'll also show you why I think it's very important, despite we have like actors and everything else today, which basically makes concurrency more accessible. All right, but first of all, let's look into why we need a memory model, or what the memory model, what problem it solves. And if you've been to my talk yesterday, not at Elton John, you could have done both, but it was a small time conflict. The reason that we have a Java memory model is that the Java virtual machine optimizes our code heavily. And in the context of concurrency, that is very difficult. The Java virtual machine tries to understand what our code is doing, but in the context of multiple threads, that is sometimes very difficult. How can you basically analyze and predict a program if potentially hundreds of threads access the same code base simultaneously, right? And what happens when we write a Java program is that we express our intent of what our program is supposed to be doing. We express that as Java source code, right? And then we hand over the source code to Java-C, which compiles to bytecode. And this bytecode is then handed over to the Java virtual machine, where code starts to be optimized. And in that context, code is transformed a lot. And basically, the memory model sets boundaries to how this code is allowed to be transformed. So if you, for example, use a lot of volatile fields in your code, what this does effectively is that it prevents the Java virtual machine of optimizing fractions of your code. So if you use volatile fields or synchronized blocks in the wrong way, this can really severely slow down your programs. And even if you don't use concurrency at all, simply because you basically forbid the just-in-time compiler to do things. Because the machine code that is basically produced by a Java virtual machine can be very, very different to the program that we have written. The program that we write is supposed to be focused on readability, on clarity, while the machine code focuses on performance, on basically running a program as quickly and as efficiently as possible. So let's look at a first lie that we like to think about when we run a program. And this lie that we all basically accept when we write programs is the lie of sequential consistency. And what I want to do now quickly is I want to run this program as if it wouldn't be optimized. So I want to explain to you why it is important that the JVM optimizes our code. And what we want to do is that we run this program on a fake hardware. So this fake hardware has a main memory where we have this instance stored in form of two fields, foo and bar, which start out with an initial value of 0, right? This is how this reordering class is defined, right? So now we want to run method. And how do you run a method or any code on a computer? We do that by sending instructions to a processor. And the processor will then manipulate the data that we have. And every program in every language on every computer breaks down to this. We have values stored, which we manipulate using a processor. The most simplest computers, even a calculator, they more or less work like that, right? So in order to add the value 1 to the field foo, we have to send this instruction to a processor. And the processor has a cache processors never operate directly on values that are saved in main memory. So in order to manipulate foo, we first have to load the value into the cache. And there we can increment the number, and then we have to write it back to main memory. This is how all data basically traverses a computer. And now we go further to the bar value. And now we do the same thing. We increment and we write it back. And now, of course, the last instruction, foo, we have to read foo again and write it back. And you can already think how you can optimize a program like that. Of course, caches are bigger than just one slot. This is just a very simple machine to make a point, right? But in a bigger dimension, this is true. If we have to swap out values from memory all of the time, this is fairly inefficient. So how can we optimize this program? Well, it's fairly simple. We can swap around these instructions. We can take care of foo first before we take care of bar. And that is where the problem comes in. This is a single-threaded program. The Java virtual machine can read the code of this method and say, okay, this switching here is safe because we don't really expect any other outcome. We don't expect the value foo to be transformed after the value bar, right? But in a multi-threaded environment, this changes state. Because if you look at the pairs that we can observe for the first program, we recognize that this third value wouldn't be possible. If we observed from another thread this object that we are writing, we would suddenly see that foo is 3 and bar is 0. And if you look at our source code here, we don't expect that to ever happen, right? We would never think that that would be possible. But this is a transformation that the Java virtual machine is allowed to do. And it will absolutely do it. This is a very simple, straightforward optimization that we can do in a room, just like that, right? The Java virtual machine applies much more complex transformations to your code than that. And that is why sometimes in concurrent programs, you observe states that you cannot explain to yourself why they can even exist, right? Okay. So of course, the Java virtual machine can even optimize this further, but it doesn't make our strange state of the object go away. This will still be allowed to create an object where foo is set to 3 while bar is set to 0. And that's a problem when we write multi-threaded code. And why is this important? Let's look at some numbers. Processes have become very, very fast in the recent years especially. And it's slowing a bit down, but again, we got a lot of free lunch. And that was important for processing speed. But the caches of processes didn't become exponentially bigger, such that this processing power is actually used by many programs. So if we look at the colored instructions here, if we can read a value from L1 cache, it takes approximately half a nanosecond before this instruction reaches the processor. And we can also read from this table that it takes on average a nanosecond to execute an instruction. That means that if we have all the values that we need to run a program, if all these values exist in the level 1 cache is the cache that is the closest to the processor, then we can actually feed the processor with enough instructions to constantly execute something. However, if we go all the way down and we go to how long it takes to read 1 megabyte sequentially from a disk, then we can see that this takes 20 million nanoseconds, right? So that means 20 million instructions cannot be run while the processor is waiting for this data to arrive. People also like to speak about processor stalling. And that's happening a lot. And you have to write cache-efficient programs in order to fulfill this premise. And the great thing about Java is that we don't have to care as much about these things as other programmers in other languages, because the Java virtual machine is smart. It analyzes our programs and rearranges our code in a way that processor caches are used much more efficiently, and that's actually adding a lot of performance to Java programs. Without such reorderings, we have to wait a lot. Processor won't do as much as they could. Another lie that we like to think about when we read Java programs or Java source code is the lie of eventual consistency. And eventual consistency is a concept that you might have heard of databases, like Cassandra uses eventual consistency concepts. But eventual consistency in a Java program doesn't exist. If you look at this program, it's a very simple program. It iterates over a flag. And as long as this flag isn't basically set to false, the program will increment a counter. And there's another method, which is run by another thread, which sets this flag to false. So we expect this program, if we have 2 threads running both methods, we expect this program to eventually stop with a fixed value for the count. However, the caching has an effect here as well. Again, the processor 1 will just read the count value, and the processor can say, or the just-in-time compiler can say, okay, this flag is actually never modified by this thread, so we can optimize a program. We'll just see in a second how. And also, processor cache 2 recognizes that it doesn't need to care about the count, right? So how can we optimize this program? Well, the just-in-time compiler can say, okay, this flag is always true, so I'll just replace the value with true, then I don't have to read it every time, and I can use my cache more efficiently. Again, of course, this is an exaggeration. This doesn't necessarily need to happen, but the Java language specification allows for it, meaning that I can write a Java virtual machine that is valid, which will pass all compatibility kits, and will do this optimization. And in some cases, the JVM does this sort of optimization also. The same thing goes for thread 2. The thread 2 might be required to write false, but since there's no requirement to ever write this value back to main memory, this might never happen. So even if like thread 1 didn't do the optimization, this other optimization might prevent this program from ever stopping. And of course, that surprises us, because if we look at the source code here, we were wondering, what's going on here, right? Okay. So, and one last lie that we like to live, which is not so important, and that's probably one you heard of before, is the lie of atomicity. Atomicity means that we consider all values in a Java program to be atomic. If I write to a field that is 64-bit long, like long and double values, then we expect these values to always be modified atomically. However, let's run this program quickly on a 32-bit architecture. That doesn't exist that much anymore, and that's why I already said this is not much of a problem anymore, but this can happen. So, we have main memory where all values are stored as 32-bit values. That's the smallest entity that the Java virtual machine, or rather the hardware beneath running our process, can read. And then we have the long field foo saved in 2 slots because it's 64-bit. And we start out with zeros, and then processor cache 1 writes back its value, which is the hexadecimal for the first 32 bits set to 0 and the last 32 bits set to 1s. And this processor 2 does the opposite with those values switched. And now, since this is not atomic anymore, what can happen is that first processor 1 gets the chance to write the first part of the field, then processor 2 gets to write the second part of its field, and then both processors get to write the missing parts back. So the value that we will observe all of a sudden will be the value for long set to all ones, which is -1. But we don't expect -1 to ever happen here, right? It's -1 because we have 2 complement notation in Java where all 1 bits equal to the value -1. All right, so this is also a problem, and these 3 problems are relevant to us writing concurrent programs. And the Java memory model basically gives us a way to communicate to the Java virtual machine that we intended this to not happen. We intended this program to run in a concurrent environment where certain optimizations are not longer allowed, such that our program doesn't get inconsistent with what we expressed in our source code. One problem when writing concurrent programs, and that's why things get more relevant, and that's why I observe a lot of failures in concurrency when I'm digging around a bit, is this, it's hidden by this table in a way. Most computers, like my computer, run x86 hard architecture. x86 doesn't profit from reorderings of loadings. Like if we read 2 fields, there's no point on x86 to read the first field after the second field. So generally, despite you cannot guarantee it, generally x86 doesn't try to prefetch memory. Then the only reordering of instructions that pays off on x86 is the reordering of writing a value with a subsequent reading a value. However, on ARM or PowerPCs, on different hardware architectures, reorderings are way more aggressively applied. So while this computer might never expose a bug to me when writing an incorrectly synchronized program, if someone else runs it, they will be able to observe it. And what's happening in the hardware world is that mobile devices like to run ARM architectures. traditionally Intel and x86 were focusing much on power, on running code fast. And even my laptop, I mean, it's plugged in most of the time, right? So if we run code fast, it doesn't matter so much how much electricity, how much power it consumes. On a mobile device, and we all know how annoying it is if your phone, if your Apple Watch doesn't last a half a day, right? So power consumption is way more important all of a sudden. And that's why hardware is shifting more. So your program that might, or your library that you write, might work perfectly fine on most computers, while when someone uses the same library on an Android architecture, it isn't happening anymore because there's another hardware. It's not a problem that Android isn't basically compiling your program in a correct way. It is basically, I don't think they have a certificate because they're not a standard VM, but let's say the Android doesn't have any bugs, it doesn't have any compiler bugs. They might apply transformations to accommodate ARM architecture better than my computer does for x86, right? And that's why we're shifting in a world where this gets more important, because just a study, and I guess this is not a secret to you, that mobile devices get increasingly important. This is how it looks like. 87% of all people have a computer, and 64% of all people have a mobile device, and that's Americans in this case, and 42% have a tablet. So there's already more people owning mobile devices if you take tablets and mobile phones together compared to computers. And yeah, Internet of Things, we have all these, you can never tell what's happening, of course, but we're shifting in a more disconnected environments where electricity is a more crucial issue than it was before. That's why I think it's more than ever important today to understand the Java memory model and what it does. Okay. So, what is the memory model? The memory model is basically, this is a rather formal definition, it answers the question, what values can be observed when I read a field, right? So I want to know what values are valid when I read, for example, foo in the example before. Can it be 3 in the context of bar being 0, which surprised us, right? Or is that not allowed? And the memory model regulates that. And that's where the academics come in, right? The Java memory model formally is defined as a set of orderings. And if you take all these orderings together, you get basically a transitive closure. I studied mathematics, so that's not so complex as it sounds. It's basically the combination of all orderings, right? But it's difficult to reason about it. So what I want to do is that I want to thunderstorm, or I guess tearing down JavaOne already, right? So what I want to do is I want to look at examples, and then we can look a small bit at the orderings, right? And one thing about the memory model is that it's not concerned with concurrency necessarily. The Java memory model is really just answering this question. What values can I read on a write? And if we read this program, right, foo is 0, then we set foo to 1, and then we assert foo to be 1. This program will always assert true. It will never throw an assertion error, right? And why is it the case? Well, first of all, probably we don't have assertions enabled, so it doesn't matter. But the memory model dictates that in a single-threaded method, that all reads of the value have to observe the values that were written before. So even in a single-threaded environment, the Java memory model has an implication. And it's basically just to get you familiar with this terminology, if you ever want to read it up, we have 2 actions. Actions are all readings and writings in a way. We have one write action and one read action, and then we have an order, which is the program order, which defines that inside a thread, the read action must always observe the previous write action. That doesn't mean, of course, that the Java virtual machine really has to set the field foo to 1 already, but that read of foo must always be 1. So the Java virtual machine is allowed here to basically simply remove the assertion altogether, because program order already dictates that that's a possibility, right? And that's why it's important to think about the Java memory model more as a way of communicating with the Java virtual machine rather than a way of influencing hardware decisions or optimization decisions, right? There are 2 ways, or 3 ways rather, to communicate your intent according to the Java memory model. And you can either communicate intents on a field scope, and there we have two instructions. You probably all know that volatile is a way of expressing something in a concurrent context. What many people don't know is that the final modifier, also have implications on the optimization that a Java virtual machine is allowed to do. And of course, synchronized, both as a method modifier and the method block, allow, besides, of course, they do synchronization, right? They do mutual exclusion, but they also decide on reordering instructions that are allowed to be performed. And implicitly, many of the classes within the Java util concurrent, like the lock, for example, have implications with the memory model with respect to reordering constraints, because internally, many of these classes in there, like concurrent hash map, use volatile fields and final fields. So what I want to do now is basically I want to walk through an example of all of these ways of communicating intent. And then I want to look at some frameworks that you probably all use. I want to quickly look at Spring and at Akka, how these frameworks solve concurrency issues. So that's the rest of the talk. It's now 40 minutes. So 40 minutes, again, it's not super trivial, but I hope it's very valuable. And then we can all have a beer. Brilliant. Okay, so that's the text to what I just said. By the way, if you want to have the slides, they're all on SlideShare. That's why there's sometimes text that I don't really expose. I always get a lot of questions on my presentations, and it reduces the noise for me to have some explanatory words on the slide. So they should be readable, and not like a book, of course, but they should give all the hints if you want to read up something afterwards. So let's look at a program which fails on many hardware architectures, not on x86, and I'll explain quickly why, but let's just look at what's wrong with this program. So what is this program doing? Well, we have a thread 1, and thread 1, basically we implemented a very bad lock, a spin lock, where we basically wait until our thread is ready. So we check the field ready, and then once we are ready, we assert that the answer is 42. And in thread 2, we set the answer to 42, which is the expected outcome, right? And after we do that, we set ready to true, so that the other thread can run the assertion and hopefully succeed. But what we just read is that the Java virtual machine can reorder these instructions. And on x86, we don't reorder normally store stores. And store stores means two writings to two fields are not normally reordered. But on other processor architectures, this can be an important optimization. In real terms, the field for ready might be in a different cache line. And maybe this cache line must be flushed to main memory before the cache line that answer belongs to has to. And then this assertion will run false, right? So it is a legal outcome, according to the Java language specification, that this assertion fails, right? So how can we solve this problem? Well, you might have guessed it, because the title of the slide says volatile field semantics, that we have to do some volatile magic here. And you might, maybe you know that already, but we don't have to make both fields volatile. It's enough to make one field volatile, in this case, ready. And if we put this modifier here, this program is not allowed to fail on any hardware architecture. So what does volatile imply in this case? Volatile implies that when one thread writes to a value and another thread reads the same value, and that value is volatile, that the certain reorderings are not allowed to be applied anymore. In terms of, and here we go back to academics, in terms of reorderings and orderings, we have a synchronization order. We have synchronization order, which is not only applied within a thread, but also across threads, where if we write to a field and read to a field, these two actions, and that's again a write action, a read action, have to be committed in a certain order. And then, if we have such a yellow synchronization order, we have to remain the program order around these fields. Practically, this means that when you write to a volatile field, that all the writes that you have previously made in the order of your program have to be visible to any program code that comes after a volatile read of the same field. So as long as both threads write and read to ready, it is not allowed to basically do the answer is 42 after setting the field ready, or do the assertions before the spinning has ended, right? So this is basically called a happens before order. And if you ever have read any article on the Java memory model, these terms pop up a lot. Synchronization order, that's between two volatile, a write and a read. And the happens before order is basically an implication that everything in these colored boxes here have to basically remain in that order. Nothing can be pushed up above the ready, and nothing can be pushed down below the ready. So that's the first thing. Also volatile means that both threads, so that's basically fixing the problem of non-sequential consistency. We have sequential inconsistency. With volatile, we fall back, right? Again, both threads must align their value now with main memory. So that solves the problem of eventual consistency. The threads that write to a volatile field have to flush all the values, both the ready value, but also all the writes before the ready value, back to main memory once they do that. And all threads that read a volatile value have to refresh all their values from main memory after discovering reading a volatile value, right? So this basically fixes the problem that we had before in the first example, where the one action would never become visible to another thread. And thirdly, if a volatile value is a type long or type double, then these writes and reads have to be atomic. So that we solved the third problem from before, the problem of atomicity, right? So these three problems are encapsulated by the volatile modifier. And of course, now you can also see the downside. These are potential optimizations that could have sped up our program. So if you go around and you just spread volatile everywhere in your program, you might fall back to a program that is run in the order you actually defined it. And that might be magnitudes of slower. That might be 200 times slower, 300 times, thousands of times slower if you just do it everywhere, right? Because this, in the end, forces the Java virtual machine to say, okay, I cannot turn these things around, I cannot put things together, which might then basically forbid other optimizations that would have been based on these previous optimizations. So don't abuse volatile. You should always know what you're doing when you use these keywords, because they seem harmless. It's just a modifier, but they might have huge impacts, right? So, and it's important, these actions have to be on the same field. If you just read any volatile field from one thread and just write to any other volatile field from another thread, these ordering guarantees are not there for you. Okay, so let's look at this problem and let's solve it in another way. This is the same code as before, right? We spin and then we assert, and the other thread we just set the answer first and we set ready. Another way of doing this would be to do synchronize, and I'm very much aware that this program might deadlock because the third thread doesn't give up the monitor anymore before the ready is modifier set, right? But let's just assume that thread 2 always acquires the log first. If this would be the case like it was before, we still don't have the guarantees that, for example, this reordering is not applied, and we don't have the guarantees that values are actually flushed back to main memory to become visible to thread 1. However, synchronization has the same effect, more or less, as volatile. It also instructs the Java virtual machine to preserve a certain ordering. A synchronization in Java is basically broken off into two different instructions. And if you look at Java bytecode, basically the first step of compilation of any Java program, you already see that actions are broken into two different instructions. And one is entering and one is exiting a lock. And you can actually, if you do bytecode manipulation, and it's a terrible idea because the Java virtual machine won't recognize this pattern, if you can break up to have basically the synchronization entering in another method than the synchronization exiting. And that forbids a lot of optimizations that the Java virtual machine expects to be doing. There was actually an entire talk at JavaOne just about this problem, more or less. So it's something severe, but you cannot do it if you just use plain Java. Again, we have a synchronization ordering here, because every time you exit a synchronization block and you enter the same synchronization block from another thread, the same restrictions apply that applied before. both threads, the first thread on the left has to flush all of its writings to main memory, and the second thread has to get all values back from main memory. We don't really have the reordering problem anymore because, of course, the synchronized blocks are mutually exclusive. So even if it was reordered with inside the block, then we would only gain control from the another thread once both actions were already committed and flushed back to main memory. So again, yes?
What exactly is the information flush? I mean, if I were to read already from another thread but without the lock,
Yeah.
am I guaranteed to see what happened on the left, on the upper left there?
Basically, all actions must be committed. That either, like, if it has you could have a side effect there, right? So you might have to basically the easiest thought you can have is it's forbidden that you are surprised. So once you exit the monitor, everything needs to be flushed. And once you enter the monitor, you have to fetch everything from main memory. What the Java virtual machine is allowed to do is that it's called a roach motel. It can put instructions inside the block, but it's not allowed to put instructions out of the block. So basically, it might do more before it flushes, or it might basically pull before prematurely, right? But it's not allowed to, for example, flush everything, flush the 42, but without flushing the ready. Yeah?
Could the answer be flushed before the ready, before you have exited the synchronization block?
No, it's not allowed. Yeah, I mean, depends on. If it's on the same cache line, it's implicit, right? But as far as I know, no. Oh, no, yes, it is allowed. Yeah, sorry. No, it's allowed. Within the synchronization block, that's basically an entity. In this case, you don't have any ordering guarantees anymore, but you have guarantees of mutual exclusion, which basically solves the first problem of reorderings, but it's not allowed to get anything out. It's basically just these barriers. You can see them as borders that you cannot cross. You can go in, but not out.
Can you repeat the question?
The question was if it can basically flush the answer before it flushes the ready. Or no, the other way around, if it can flush ready in this case without. So if you basically have one thread that synchronizes and another thread that doesn't synchronize, you don't have the guarantee. Then you can, again, observe in the wrong order. Okay, so and again, it's based in the formalism, it's based on synchronization order in combination with program order. And basically what the transitive closure means is that we can connect errors. That's really what transitive closure. My mathematics professor wouldn't be happy with this explanation, but for now it's good enough. Connect the errors, that's transitive closure. All right. And from that we derive what is the happens before relationship, which we desire in order to make this program correct, right? Okay. Blumps. So there's more actions than that. That's the main actions, but let's look at that one. We start a new thread, and then the first and only action of the thread is to assert that the value foo is set to 42. We don't use volatile here, important for this example. Are we guaranteed that this assertion never fails? Well, we are. That's color. The reason that this is guaranteed is that every thread in the terminology of the Java memory model starts with the first synthetic action, which is the start thread action. And we have a synchronization order between the action that starts the thread and the start action. So any thread that we start from a thread basically copies all the values into its cache, which are already observed from the other thread. In this case, this is foo. So again, we have program order, synchronization order, we connect the dots, and we end up with the happens before relationship, right? So also here, we don't have to explicitly synchronize, because of course we could maybe never read 42 again, but we can start a new thread, and it is guaranteed to see the world as we see it from the starting thread. Okay. Let's look at final field semantics. And we're solving another problem here, which often occurs in the context of double-checked locking. We're actually going to look into double-checked locking as an example of application of the Java memory model in a short while. Let's look at this example. What we do here is that we create an instance of unsafe publication, and it's already spoiling the outcome, of course. And the question is, can this assertion ever fail? Right? And the answer is, of course, yes, it can fail. And important here is that we only assert in cases the instance isn't null, right? Otherwise, we could get a null pointer here because thread 1 might run after thread 2. But it might be that we observe the instance in a state where it's uninitialized. And the reason for that is that initializing an object is broken off into two actions, or to multiple actions, actually. The first action is the pure object allocation, basically writing an object to the heap, but without having executed the constructor yet. So the constructor, in this, I refer to it here as init, which is also the bytecode representation of a constructor. But constructor, in a way, is just a method, nothing else. It might run after the instance was already allocated, but before the assertion might run after allocating the instance, such that the if instance is null returns false, right? True. And then we run the assertion, but init wasn't run yet. So assertion, asserts to false and throws an exception, an error in this case, right? So how can we prevent this? And again, the title of the slide says in a way what the problem is, what solves the problem, and is setting this field final, right? The thing about final fields is that we have a so-called freeze action at the end of a constructor. Once we set a field final, the Java virtual machine basically is not allowed to publish an instance to another thread before setting this field to the value it receives in its constructor. So once a field is marked as final, you can rely on the object being fully initialized in all other threads when it is observed, right? Yeah?
That applies, so if you, I'm just making sure I understood what you said.
Yeah?
You're saying that if you have one final field, then every other field
No. I mean, practically the implementation, if you look at the source code of Hotspot, that's what it's doing. And sometimes you see people wanting that behavior, so they just have a field dummy, final field dummy is object, right? That's terrible, because I can implement a JVM, which just wants to annoy people that do that, which legally, publishes instances very badly, right? Delays every initialization action and just sits there for a minute and waits other threads to fail. So this is only true for final fields. So if you have two fields, right? One is final and one is not final, and you assign the same object to both fields, the one object might be there already, and the other one might not be there.
in a hypothetical VM.
Yeah, in a hypothetical VM. Yeah, I mean, that's the thing about, I'll have one slide on that matter. You should always code against the specification, never against the implementation of Hotspot. Unless you do like high performance work, and I know people that do that, they run around implementations. But what that basically requires you is that whenever you upgrade Java, even if it's just a security check, security update, you have to look at the implementation again, run all tests, see if everything works again, because you did something that is technically not allowed, right? So the freeze action is only true for the field instance foo here. So that introduces not a synchronization order. If you, again, look up the Java language specification and read the formalism, this is referred to as a dereference order, not a synchronization order. But this basically says that this constructor has to be executed as a whole. So it is allowed to see the field as null, even though it technically already happened, but it wasn't flushed yet. But once you flush the instance allocation to the heap, you also have to flush the information about setting this field foo to 42. So then again, by setting this field final, the assertion will never fail again. And if you pay close attention, this happens before ordering, doesn't cover the entire code this time. It only covers the constructor, right? So once you allocate it, the freeze action, which is basically the freeze it on the heap, make it accessible to everybody else, this has to happen before another thread can observe this object. Yeah. Yes?
What about writing to instances the fields that are inside the object?
Yeah. There's another ordering that I didn't fit on the slide. Basically, once you walk through a final field, all references that you make through that final field are visible. So, and that way, in theory, you might observe an object in two states. Once fully initialized, because you dereference the object via a final field, and once partly initialized. And that sounds like it's impossible, but it's possible. If you look at C2 compiler, what it does, it's crazy. It's really 20 years of crazy performance work, right? There's a lot of things you might not expect to ever happen, but I spend a lot of time on trying to understand what hotspot does, and I'm still apprentice level, despite I'm doing this for years now, right? Yes? Yes, of course. If you basically read the field from another thread, which isn't in a synchronized block, if it was in a synchronized block with the same monitor, the code couldn't run yet, right? And once you exit the monitor, then you have to see the field fully initialized. But and that's the problem of double-checked locking. We'll look at this in a second. All right, so here's text again. So there's more actions than that. One is external actions, and that refers to JNI. So JNI, basically, let's say we implemented a native method which asserts that foo is set to 42. Could the just-in-time compiler reorder foo and the JNI call here? The answer is, of course, no. And that's what makes JNI so dangerous, and that's why JNI is considered to be slow. It is simply because everything that JNI does is not known to the just-in-time compiler. The just-in-time compiler cannot read native code, right? So basically, it has to assume the worst. It has to say, okay, this JNI method expects the world in a state how it was basically described here. So external actions basically say, you can never reorder these things. This has to remain in program order. And JNI is more than you think. JNI might be system out println, right? That's native interaction. Because you don't want anything on the console that describes a state that wasn't supposed to be there, right? So that's why like logging frameworks, they basically write everything to a buffer, and then they pull from the buffer to read it from the console from another thread. Because that's better for optimization. Otherwise, you have these native blocks everywhere. That's really important. If you have any like random system out println that you have maybe just with an if something is enabled, right? If the JVM cannot prove that this code can be deleted anyway in your production environment, that might refrain from optimizations that you could otherwise do, right? Same is for I/O. If you have performance-relevant algorithms, for example, it's always good to make these blocking actions from another thread and to pull something from a buffer. It helps the just-in-time compiler sometimes, right? But that's micro-optimization work sometimes. So be careful with what you optimize, but it's good to know this stuff, right? Okay, and there's another rule, that's the last rule, that the thread divergent actions, again, is this program allowed to assert false and throw an error? And of course the answer is no. Thread divergence actions basically means if the JVM says, okay, this action will probably never be reached, then I cannot execute it, because we would be confused if foo would be set to 0, despite the field not being volatile, because we effectively prevented this action to ever happen, right? That's basically what thread divergent action means. I name it with the academic expression because if you read through articles, through the Java language specification, you will see this, right? Okay, Blumps. So in practice, double-checked logging. If you don't know double-checked logging, basically it's lazy initialization, right? So what we want to do is that we have a singleton object and we want to initialize it lazily, right? Because the constructor has some expensive some expensive initialization procedure. Maybe it goes to a database or something. And of course, we shouldn't do that, but we don't know in general, right? And what we want to do then is we want to check if an instance is null, and then we synchronize on this instance, right? Because all instances are received via the getInstance method. And then we check again if the field is still null, because maybe another thread did the same routine and already initialized the instance before we even reach the synchronization block. And then we set the instance and then we return it, right? And if you paid attention yet, you know why this can fail, why this assertion in method can be 0. And it is because allocating an instance is not implying that all fields and the constructor is already run, right? So we might have written the field from one thread, and then basically we had a context switch. That thread was delayed before even executing the constructor. Then another thread came in. It checked, okay, instance is not null anymore, so I just return it. And then I basically expect foo to be 42, despite that the other thread didn't run the constructor yet, right? And then we have an assertion error. So basically, we haven't gained anything. If we would have always entered the synchronized block, and we didn't in this case because the instance already was allocated, then this problem wouldn't occur. So here, I have color here, right. So what we have to do basically is that we have to make this field volatile, right? And only then we have an ordering guarantee that implies that the constructor has completely run, because at one thread we write to the field, right? And from another thread we read from the field. Implies a synchronization order, implies that all the writes from the one thread are visible to all the reads of the other thread. So this is the only valid way of doing double-check locking. Yes, sir?
That instance is static, but then you synchronize this. I don't
Yeah,
think this is available.
you're right. It should be on the class, so it should be on double-checked. Yeah, you're right. Good point. I'll fix it later. Right. So, and this has really bad reputation, right? In some cases. Yes?
Did you fix that by assigning it first to a local final variable and then doing the assignment out instead?
If you have, there's different patterns to making this safe, and one pattern is final field wrapper. So what they do is basically they, instead of assigning the value directly, they have like a generic object called holder, and then that has a parameter t, right? So you basically create a constructor which has a final field of parameter t. You assign the instance to that field, and then you only read the field via the instance. By going through the final variable, you are again guaranteed to see all fields initialized. There's an overview, there's a great, I hate to always quote Alexei Shipelev in all of my talks, but he has great resources, and one is about safe initialization, where he compares the performance implications. The problem with that approach is that it runs often faster, but not on all hardware architectures. So you can, again, micro-optimize for certain processors, but you don't want to go there. That's one of the reasons we use Java, right? We don't want to think about these things. The fastest way, actually, is always to do something in an enum. So a field of an enum is implicitly available whenever you read the enum. If the enum class is read lazily, then we basically have the same effect. We initialize the single instance lazily, but what the cost that we have is an additional class, right? But the same goes for holder. That's why I personally prefer double-check locking, because today on modern hardware architectures, volatile reads are more or less free. Volatile writes have a minimal performance overhead, but volatile reads don't. At least on x86. It's not true on ARM, but you have to get it somewhere, right? So, but the cheapest way is enum initialization. Actually, Scala, this is what Scala compiles to in bytecode when you use the lazy keyword in Scala. It's double-check locking in exactly this form. If you do this yourself, just never forget volatile. You will be able to observe the strangest things, right? Okay. Another common problem that I see in practice is, that's the practice element part now of the talk, is that people make arrays volatile. The problem here is that we have the array volatile, right? And then we have the same problem as before. We read a value from the array, and then we basically have another thread that again sets the answer and sets the flag in the array. The problem this time is that the volatility really only concerns the array itself. Here, we once read array for getting ready, and then we read it again to set it, because we read the array, but we set the value on the array. And that's a different thing, right? And this time, we have two reads of a volatile field, and two reads, other than a write and a read, they don't have an ordering implication. So here again, the Java virtual machine is allowed to optimize code and to flip things around. So once, and people like to use, like they have a distributed job, right? And they write results of each thread through an array element. And they think that by making that array volatile, the results of other threads gets visible, right? That's not true, because the elements of an array, there's no way in Java to declare array elements to be volatile, only the field references, right? And you cannot go into an array and make fields in an array. So what the Java virtual machine has instead, it has a so-called atomic integer array. And in atomic integer arrays, you can make volatile reads of elements. You basically give the array to an object instance of atomic integer array, and then under the covers, the Java virtual machine, at least Hotspot, uses the unsafe class, but in a safe way, right? So you are allowed to access field values. And I think in Java 10 we will have var handles and all these fancy things, hopefully. Then we can do that, but right now we don't have a way other than having a wrapper class. Okay, I have 10 minutes left. We're almost through as well. Let's look at some practical implications. Do you think that is safe? We have a Spring Bean, right? And Spring typically is in a multi-threaded environment, right? We have controllers somewhere, we have a web application, and our web application accesses repositories and all the like, right? However, many people in Spring like to do setter initialization and have like post-construct annotated methods, which are then run after the Spring context was set up. So we wonder, can this assertion, if it's triggered from another thread or at any time be false? Like, can these values be not set? And the truth is no, it's not possible for Spring. Everything you do in the initialization phase in Spring or any well-written dependency injection framework is guaranteed to be visible to all threads later. Of course, internally, Spring doesn't have a magic trick that it can use to do that. But what Spring does is that it writes all beans to a volatile, through a volatile value, and then whenever it hands a bean over to another instance from another thread, it will read the beans over this volatile field. And that way, the Java memory model guarantees, in a way, that foo and bar are fully initialized once you have reached your actual application after the initialization phase, right? And this is only true for initialization. If you have a Spring Bean and you mutate the values, then a multi-thread application, again, is allowed to do reorderings and to see values in a certain way. Because just-in-time compilation doesn't work like it's happening at some point, and then it never changes. It's dynamic. It's basically adaptive. It looks at how your program is like right now, and it might do rearrangements even after the initialization. So don't rely on it. If you have initialized something, Spring gives you extended guarantees similar to final fields or to volatile values. You don't have to make foo and bar volatile here. But it only works for the initialization phase. Afterwards, you own your own in a way. And then you don't even have the reminder of a final field, which is even disallowed to be changed, right? Okay, same goes for actors. ACA actors, I take this as an example now, are not guaranteed to be executed from the same thread for all messages, right? So how does ACA do it? In this case, we write foo to be 42, and then we send a new message to ourselves to trigger the assert. ACA does the same trick. ACA basically writes all actors to a volatile field once a method is dispatched, and if another thread has to execute the same message, this thread reads the same actor back from this volatile field. And then under the covers, of course, we have again an ordering, read-write, and you can argue that it's easier to just accept that ACA does everything for you, but there's basically no trick. ACA isn't faster because it does something magically, right? ACA is just using the primitives given to you by the Java virtual machine and by the Java language specification, rather. It's by the way, a nice thing to know. Most Java JVM, the memory model is a model specified for Java, the programming languages. Most programming languages that compile to Java bytecode don't have a memory model, a well-defined one. So basically, you just have to accept how does this map to bytecode, and then you can use the Java memory model in a way, right? Okay. So, yeah. One thing that I see sometimes, right? How the Java virtual machine implements the memory model is by using so-called fences. Fences means that whenever it encounters a volatile write, it will just flush everything. And once it encounters a volatile read, it will just pull everything from my memory. And I said before that we have to read and write the same field in order to have these guarantees. In hardware and practical applications, this is way too complicated to check. So in most cases, like here, we can just say, okay, we synchronize on a new object. That means, of course, we enter a monitor, we exit a monitor. This is like flushing memory instruction, right? And you see that. I've seen this way too many times in library code and libraries that everybody uses partly, because this worked out. However, the JVM becomes smarter every day. So that's why I'm telling you, code against the specification, not the implementation. Because the JVM, we can say that, right? So the JVM can say that, to say like, this is nonsense, I removed this. And then you lose your guarantees, right? So don't rely on these things. Okay, we're almost through. Just quickly, if you want to prove correctness of a program, what do? We take all these orderings I've shown you, you basically lay upon them, and you have the small intersection where you say, okay, This is the only value that's allowed to be observed at that point, so I have a correct program. I just proved it. And again, my mathematics professor would love this. This is how you do academics. But for us as practitioners, that's not feasible, and it's really hard to prove as well in real programs. So what I can recommend you is a framework called JC Stress. Again, I mentioned him way too much, so probably he should give this talk, but he doesn't, so I just can refer to him. Alexei Shipilev has written a framework that basically runs a lot of load on your program, and it basically tries to trigger scenarios where reorderings cause weird states. So basically what it does, it runs this code millions and millions of times, and then it checks all the outcomes that you write to int result. And then it will tell you, okay, you know what? This R1, this result that I've written, it was 99.9% of the cases, it was actually 42, what you expected. But these 4 or 5 times, I have encountered the value 0. And that's because, optimizations aren't deterministic. Sometimes things are triggered in a certain way. The framework basically tries to push your JVM to do optimizations as much as it can. And this is, of course, not a unit test, but it can discover problems in your code. And the problem is that it only tells you have a problem. That's sometimes not enough, but that's why the memory model is hard, right? Problems, just a quick look before we're done. In the future, the Java memory model is currently under revision. The atomicity guarantee doesn't make much sense anymore for 64-bit machines. And everything today is a 64-bit machine almost. So that's considered, because you can't do, you can't just get the volatile part, the atomicity part of a volatile field. You have all the guarantees, which is, of course, much costlier than only applying atomicity. So probably in the future, we will see the memory model to be revised to encapsulate that. There's also another funny thing is that you cannot make a field both final and volatile, right? You cannot guarantee that it's in a certain state after running the constructor, but still have it mutable in a concurrent context. And that's a problem to many people. So also there's revisions over how the memory model will be revised. It was already revised in the past once. JMM 133 was that. Before the memory model was broken. So if you run old Java virtual machines before 1.3, you have to be super careful how you write your code in a concurrent environment for various reasons, right? Okay, data races, we stop over that. Basically, it says the Java virtual machine, if you have data races, at least the Java virtual machine has to give you a value that makes sense. It cannot make up stuff, right? So just that slide. I know I want to leave, you want to leave. That's it for me. Thank you so much for coming. My name is Raphael. Yeah. I'll be here 5 minutes more, 10, or however you want, basically. I'm flying home tomorrow. So if you have questions, just come forward. You find me on Twitter. I have 2 open source frameworks that I try to promote. One is ByteBuddy, which I talked about on Monday. Just won a Duke's Choice Award on Tuesday. It's a lot of work, and it's really cool application, so check it out. Documents for Jay as well. Thank you so much. Bye-bye.